Good morning, everybody, and welcome to our Thursday session for, I don't remember which week we are in right now, so I lost track of things. Anyway, we're continuing chapter 41. I already posted the first half of chapter 41 on Canvas, so hopefully you guys have had the chance to go through it. Basically, what chapter 41 is, grab the book. It takes what we learned in chapter 14, namely Schrödinger's equation in 1D, and basically takes it in 3D. So this the problem becomes a little bit more complicated in the sense that you have to deal with so many variables, and that is a more realistic problem anyway. So the first part that we did had to do with the particle in a box. And that is a generalization of the idea of a particle basically in a box in 1D. In 1D, if you guys remember, you really had those standing waves similar to what you did in for a string that is fixed on both ends. And then you have the different modes of vibrations of that string. You will have one antinode and two nodes, two antinodes and three nodes, and so on and so forth. So that's exactly what happened also in this case. You have stationary solutions, and the reason why they are stationary solutions is because we already have accounted for the energy of the system with the temporal behavior. So we're just focused on the spatial behavior. Okay, so we impose the boundary conditions that the wave function must be continuous at the boundaries. Since the potential on both sides is infinite, that means the particle cannot exist outside, doesn't have enough energy to be outside of that box, at least in the 1D. In the 3D, actually, it's a little bit more interesting in this situation because it's similar. You have confinement in the x direction, you have confinement in the y direction, and you have also confinement in the z direction. So it's the same thing. We did a separation of variables basically for the wave function psi, and we wrote it as a combination or the product of three functions, namely big X that depends on little x only, and big Y that depends on little y only, and big Z that depends on little z only. The energy in this case is still included in the time behavior, so that was factored out. That was part of the process to get rid of the time so that we are dealing only with space. In other words, we took the normal Schrödinger's equation, we wrote it with a time-independent version, and that's what we're dealing with. We're dealing with a time-independent version, and at the end, the solution actually gives you those energies, E. And so basically, it gives you a solution also for the time, okay? Because it's exponential just of negative IET over h bar. So the T is there when you multiply by E for it. So that's the frequency, if you wish. Omega E over h bar, that is omega, okay? Because again, we use the Euler conversion to convert that exponential into a cosine and sine functions if we want to convert it into something. Because at the end, we're going to get the real part at the end because we're going to get the probability density, which is a real function. Anyway, so this is basically what we dealt with in the 3D. Here is one thing I didn't mention. It's critical, actually. It's very, very important, okay? And we don't really go in detail in it in this class, even in the book itself. The fact that those functions that we found for the 1D or for the 3D, it doesn't matter. For any problem involving Schrödinger's equation, all the functions, they satisfy two relationships for different ends, of course, for different quantum numbers. They satisfy two different conditions. The first one we already dealt with, and that is the normalization, meaning you take the amplitude squared and you integrate it throughout the entire space, you must find one. That means there is a 100% probability that the particle exists somewhere. It doesn't matter where, it exists somewhere. So that is what that condition is. So we impose that that probability is 100%, meaning that the modulus of that function, when you integrate it, is equal to 1. Similar to what you do in vector space, normal vector space. You have I, J, and K. Those are actually unitary vectors, meaning their length is 1. So I hat times I hat is equal to 1 times cosine of 0, which is 1. So it's length 1. J also is of length 1. K also is length 1. So these functions, they are unitary in this sense. They have basically, when you sum their probabilities, they're individual, not all of them. Each and every one of them for different quantum numbers, you will find 1 because the particle has to exist somewhere, okay? So that is condition number 1. We dealt with it already. Condition number 2, and I didn't really prove it, but it's really kind of long to prove. All of these functions, when you cross product them, meaning you take 1 for one value of n and a different one for a different value of n. It's the same way of functions, but they have different indices, different quantum numbers. And if you try to form the product, you're going to end up with an integral that is 0. So what I mean by product, I take the complex, because they are complex functions, I take the complex conjugate of 1 and multiply it by the second without taking its complex conjugate. So one of them is in complex conjugate form and another one is in itself, and then integrate throughout the entire space. If I do that, all of these functions, as long as the indices are not the same, will give me 0. The integrals will be 0. Similar to when I take the vector I and dot it with the vector G, because of the cosine J, I mean, the cosine of the 90-degree angle, that dot product is 0. There are 2 normal vectors. I hat is in the x direction and j hat in the y direction. So if I take the length of the first one is 1, the length of the second one is 1, cosine of 90 degrees, that is 0. So this is called the orthogonality. So in a similar fashion, those solutions to all of the Schrödinger's equations, they're also perpendicular in this sense. So what I'm trying to argue in here is that the vector space, the 3D vector space that we know, has a counterpart using the solutions to Schrödinger's equation, where I take any function that you can think of, anything, is just a combination, a linear combination of these solutions to Schrödinger's equations. Granted, there are not only 3, there is as many as n, since n can be infinite. So there is an infinite, basically, projection throughout all of this space. This has a name in quantum mechanics. They call it the Hilbert space. We don't really go in detail about this one in here, but sometimes it comes in very handy, because when I take a measurement, for example, when I'm trying to measure a quantity in quantum mechanics, property, it doesn't matter, the position of the particle, for example, or the momentum of the particle, for example, or I'm trying to measure, for example, the square of the position, for example, trying to find some sort of a deviation of some sort, or the energy which is related to the momentum squared, and things of this nature. When I take that, I always have to take that, the state of the particle at that point, which we don't know. It should be a linear combination of all of those solutions that I have found. Similarly to when I'm taking a vector in 3D space, it has 3 components in the x and y and z directions. The state of particle is also the combination, the linear combination of all of these states. When I make a measurement, I will only find one value. And that value indicates that that state that I was undefined for the basically linear combination of the different states that I found, the different solutions that I found, collapses on one of them. Otherwise, it's really still a linear combination of all of the different solutions. So it's an important aspect, and we talked about it actually. I didn't mention it in detail, but it's actually in chapter 40 toward the end, talking about the measurement and the interpretation of the wave function collapsing on one of those solutions. Because when you do a measurement, for example, for the energy, you're going to find one value. You're not going to find different values, which is for different values of n. So that is something important. And this is true also in the case of chapter 41, because those ideas are taken from chapter 40 and actually extended here, except now it's a little bit more complicated because you have to deal with the 3 components in space, x, y, and z, in addition to the time. So you have these 3 things that you have to deal with. So what we did actually in the recording, if you guys have had a chance to go through it, if not, you really have to, is that we took a particle in a box and we solved for it. And we found that the energy depends on 3 quantum numbers, nx, ny, and z. Those are integers. And you can choose them independently from 1, 2, 3, 4. Okay. So if nx is 1, ny can be 1 or 2 or 3, whatever you like. And z can be 1 or 2 or 3 independently of the others, and so on and so forth. This led to an idea. Let me share the screen with you guys so that you can see what I'm talking about in here. Let me find it first. I found it. There it is. Let me share the screen. Here, I have nx, ny, and z in the energy itself. So the energy depends on these three quantum numbers, nx, ny, and z. This is just a scaling factor. This has the dimensions of energy. This is similar to what we did in the 1D, except we didn't have 3 of them. We only had 1 of them. Okay. So in 3D, 2 more popped up. Because L is the same, when I'm taking the cube of length L, depth L, and height L. So in this case, the same L appears everywhere, so it comes out as a common factor. And there is an idea in here of the degeneracy. So what is a degeneracy in this case? If I choose, for example, this one to be 1, and this one to be 2, and this one to be 1. If I add up the numbers in here, obviously 1 squared plus 2 squared plus 1 squared is 6. So they add up to 6. If I choose this one to be 2, and this one to be 1, and this one to be 1, and namely nx is equal to 2, ny is equal to 1, and nz is equal to 1, they too add up to 6. Because 2 squared plus 1 squared plus 1 squared is 6. If I choose another quantum state where I have 1 for nx, 1 for nz, and for ny, I'm sorry, and 2 for nz, that too add up to 6 times this factor in here, whatever that number is. Okay, so that is the degeneracy. Those are different states completely. They're not the same thing. They have absolutely nothing to do with each other in terms of, because one of them doubles the x. This is 2, 1, 1. Obviously, sine 2x is not the same as sine x, like this function, the second one. So those are 2 different functions completely that depend on x and y and z. But this one is the same in terms of energy. They all have the same energy level. They all sit in here. They're all actually the same number in here, 1, 2, 1, and 1, 1, 2. Okay, so they all add up to the same energy. So they have the same energy. One way to lift this degeneracy is, for example, one way to remove the degeneracy is to take a non-symmetrical shape. Basically, take a cube of a length, and not I don't know what's the name of it. So of a length, for example, L1, height L2, and depth L3. If you do that, then of course the solution will be different, because you will have in here divided by L1 squared, divided by L2 squared, and divided by L3 squared. And that solution, then if you choose different numbers, it's going to be different energies. Because the value in here divided, so if this is 1 over L1 squared is not the same as 2 over L1 squared. So generally in this case, you're not going to get the same answer. So the energies will not be the same. So you have lifted the degeneracy by removing the symmetry. So that is really what this thing is in here. Okay, so if you break the symmetry of the system, the degeneracy is lost. If there is symmetry in the system, the degeneracy is there. And this is common true. So this is true all the time. So whenever there is a symmetrical problem, then in this case, you will have degeneracy of some sort. How to remove the degeneracy in this case? By basically removing the symmetry in the problem. And if you find somehow 2 values of the energy identical for different quantum numbers, then in this case, you might have some sort of a symmetry that you're not seeing clearly, but it's in there. So there is a connection between that, okay? Another reason why symmetry is important, it's because symmetry goes hand in hand with conserved quantities. there is a theorem in mathematics, actually math physics, that basically by neither, I think neither her name, or I don't know how to say her name exactly, but basically she proved that when you have a symmetry in a problem, you will have a conserved quantity. Symmetry in translations leads to conservation of momentum. Symmetry in space and time leads to conservation of energy. So there is a theorem. So when you see a conserved quantity, when you see a symmetry of a problem, that means there is something big going on in the problem. So that is really why this result is important. I want you to remember this result, guys, because in chapter 42, we're going to need this one again, this result for the energy for a particle in a box. Okay, so this is an important result, although it's a classical, easier problem to solve than the hydrogen atom, for example, but it's actually an important result coming down the road to understand solid state physics. So this is what we did last time. And then we started with the hydrogen atom. The hydrogen atom, the equation for it becomes ridiculously complicated. Okay, and we're not going to even attempt to solve it because it's outside of the scope of the math that we have. The problem first is that the potential energy in that case is easy. Potential energy has a symmetry already in it. Namely, the potential energy for the hydrogen atom is just -1/2 of 4 pi epsilon naught times the product, the charge squared divided by the distance. That's it, between the electron and the proton. So this is the potential energy, depends only on R. It doesn't depend on theta and phi. And that is why, I mean, somebody else might want to use the Cartesian coordinates, which is -1 4 pi epsilon naught e squared divided by the square root of x squared plus y squared plus z squared. Obviously, you could proceed with the Schrodinger's equation in that case, but then, and then you have one for x, one for y, and one for z. But then it's too many problems, too many things to consider, because the problem is symmetrical, has spherical symmetry already. So you will get conserved, you will get degeneracy along 2 quantum numbers because of that. Obviously, it depends on R. Okay, so one of them will not basically be degenerate. So in other words, the energy at the end depends only on R. Okay, so in other words, 1 quantum number. And sure enough, the solution to Schrodinger's equation, if we really proceed with it, will give me the same result as we did with the Heisenberg solution, -13.6 electron volt divided by n squared. So that is the energy, depends only on 1 quantum number. It doesn't depend on anything else. But there is a condition here. There is the theta dependence and the phi dependence. The phi dependence is easy to solve because it's just the harmonic oscillator equation. Solving it will just give me the cosine and the sine. If I write them in terms of the exponential, this is how they look like. The cosine and the sine are periodic functions in terms of the azimuthal angle. I don't know if you guys, did you guys did the spherical coordinates in your math classes or not? Anybody remembers? Yes, no? You take from the x, y, z, and you put the r, theta, phi.
Personally, I didn't do that.
Okay, anybody else? From Calc 3.
Sound familiar.
Sounds familiar. Okay, so let me then, because I thought that this was covered somehow in your math class, let me give you an overview of how the spherical coordinates work, because it's critical to understand what's going on for the hydrogen atom. Okay, so again, instead of using, you're familiar with polar coordinates, I'm sure, because this is an extension of that. So basically, instead of using the x, y, and z coordinates, we're going to use a spherical coordinates. So what the spherical coordinates are, you take the same vector. This is the same vector r, and you project it into the xy plane. The component in here is your x coordinate. The component in here is your y coordinate, and this coordinate is going to be your z component. So the vector r in Cartesian coordinates is x, y, z, And in here, it's defined by this angle theta with the z-axis, and defined also by the projection on the xy plane. It's this projection by the angle phi with the x-axis. So that's another one, and the length of the vector itself r. So the same vector now becomes in spherical coordinates represented by r, phi, and theta. Oh no, I'm sorry, r, theta, and phi. Doesn't matter which one you call first. I think it matters, okay, because of the right-handed rule. Okay, so this is the vector, same vector as before, okay? So in other words, it has a unit vector in here, r hat. It has an azimuthal angle in here, phi hat, and it has another angle in here, which is, this is the azimuth, the other one is the latitude, theta hat, okay? So these are the different directions in the polar coordinate, the spherical coordinate. It's easy to show that the projection of the vector r is r sine theta, because this is the opposite to this angle theta. This is the opposite to theta. This is actually the projection on the xy plane. So again, it's r sine theta, and when you project it again on the x-axis, it's going to pull a cosine phi, and on the y-axis is going to pull a sine phi. It's the opposite to this angle phi. So it's r sine theta, sine phi. And in the z-coordinate, so this is your x, this is your y, and the z-coordinate is just the adjacent to the angle theta. So it's just r cosine theta. Okay, you square this number, and when you add them up, the cos squared plus sine squared will be just 1, and you will end up with r squared sine squared, and in here plus r squared sine squared, which is the same thing after you factor out the cos sine squared. So you're going to remain with an r squared sine squared. When you add to it z squared, it's going to be r squared cos squared plus r squared sin squared, which is just r squared. So in other words, you can clearly show from this relationship that r squared is still x squared plus y squared plus z squared. So that is one way to transform back, if you wish. If you know x, y, and z, you can find r, which is something that you know from before, from the Cartesian coordinate. This is another version of the Pythagorean theorem. Another also relationship that is useful in here, if you take x squared plus y squared and under the square root, you will end up with an r sine theta, because cos squared plus sin squared is 1. And when you divide it by z, again, you can clearly see that the r cancels and you will be left with the sine over cosine. So this is your tangent theta. So in other words, you can produce theta also using this relationship if you know x and y and z. The last relationship is clearly from y over x. Sine theta and sine theta cancel, r and r cancel, but you will be left with sine phi over cosine phi, and that is tangent of phi. So the other relationship in here is that you can find phi by using the arctangent of y over x. So in other words, you can go from Cartesian coordinates to these coordinates. Having said that, then the reason then we can get rid of this representation of the potential. It's way up, so I'm going to rewrite it. That's all. So the potential looks like I'm going to write it as u of x, y, and z instead, which is really negative 1 over 4 pi epsilon naught times the square root of e squared over that square root of x squared plus y squared plus z squared instead, which is just r from this relationship. I'm going to use it as u, which depends only on r now, doesn't depend on any of the other variables. Just negative 1 over 4 pi epsilon naught, the distance between the proton and the electron. The proton in this case is just supposed to be stationary. Otherwise, I have to use the reduced mass in Schrödinger's equation. And reduced mass is practically the mass of the proton. The mass of the electron, I'm sorry, because the reduced mass is the product of the two masses. Mass of the electron times the mass of the proton divided by the mass of the proton plus the mass of the electron. And this is practically the mass of the proton when you add them up, Because remember, the mass of the proton is 1,980 times greater than the mass of the electron. So practically, this sum is just the mass of the proton. So it's the mass of the electron times the mass of the proton divided roughly by the mass of the proton. Cancel that in this. So the reduced mass is that of the electron. So at the end, you're making a mistake of about 1 or 2% if you assume that the reduced mass. The proton is not really stationary, but it's also wobbling around the center of mass of the two systems. Okay. So this is basically the problem at hand. So Schrödinger's equation now comes in handy to write it actually in polar coordinates. When you do that, you already have solution for the energy, which is similar, identical to the Niels Bohr's model. So this is exactly negative 13.6 electron volt. Oops, what did I do in here? Negative 13.6 electron volt for the energy divided by n squared, where n is the principal quantum number. Now, two quantum numbers come in here because remember, Schrödinger's equation is only one equation. So what I do in this case is the function psi that's supposed to depend on now, instead of x and y and z, depends on r and theta and phi. I'm going to write it as the product of a function that depends only on r, and a function that depends only on theta, and a function that depends only on phi. And I do my separation of variables. So this term in here, L times L plus 1, is a linkage term between the R and the theta, and the term ML squared in this case is a linkage term between theta and pi, and this is by itself. So this is in a nutshell a rundown on how these equations will break down when you do this change of variables and when you go about solving it. And except that the Laplacian in this case looks a little bit awful. But this is the equations of how they look like. We're not going to solve them. They involve Legendre functions, and they are really not something easy to work with. At the end of the day, this one gives me condition on ML, because phi changes from wherever we are, and that circle, remember, phi goes from 0 to 2 pi. Theta goes only from 0 to pi. And R goes from 0 to infinity. So in this case, I have described the full sphere. If I take a ring, this ring, and make it bigger and bigger until I reach 90 degrees, I am here. And I make it smaller and smaller until I come in here, then theta would have actually varied from 0 to pi. I have completely described the sphere in this case. I do not need to make theta go from 0 to 2 pi, because if 0 goes to 2 pi, I would have described the ring twice. I would describe the sphere twice, because then I'll have to go back and this description, and then I have overstated my problem. So theta actually varies from 0 to pi, that's all. Phi varies from 0 to pi to give me that ring, okay? That goes throughout the entire sphere. Okay, so then I have described the problem that I started with. Remember, when you do change a variable, you always have to worry about the boundaries of integrations, where they go. This is the same thing. Okay, so x goes from negative infinity to positive infinity, y goes from negative infinity to positive infinity, z goes from negative infinity to positive infinity. In this case, r goes from 0 to infinity. It still describes the space if in case I take phi and make it go from 0 to 2 pi, and theta goes from 0 to pi. Okay, so that's the whole problem is fully described this way. So here's a problem with phi. If it goes from 0 to 2 pi, that means that the electron in this case goes a full circle, comes back. The wave function should not change if I change this value by 2 pi, because I'm back to the same location from where I was. If r is fixed and theta is fixed, then wherever I was on that ring, I came back to it. So the wave function should be the same. So if I calculate psi squared in this case, where everything is the same, then phi need to also be the same, because that's the only one that changes. So it needs to be the same. So that imposes a condition on ML in here, because ML would have changed this whole argument in here of the cosine or the sine would have changed by 2i ML times pi. Of course, remember phi was phi naught, for example, and now it's phi naught plus this number. So I'm imposing that this number has to be a multiple of 2 pi, because that's the periodicity of any trig function, and these are trig functions. Okay, so that means ML can be an integer. It can be 0, or it can be a +1, or it can be -1, or it can be +2 or a -2, and so on and so forth. So ML has to be an integer for the function to be the same. So the function has to be periodic in this case. So the function has to be periodic. That means ML can be 0, ±1. So what does a negative mean? The negative means that I want in the opposite direction, that's all. Instead of going clockwise, I want counterclockwise. So that's what that number means. So it has a meaning, and ±2 and so on and so forth. So that is the easy one of the quantum numbers that we can find. Okay. Then I take that condition and impose it in here, and I find that there is a constraint on ML and L. ML turned out to be constrained by L itself for this equation to have meaningful solution, meaning that the sine theta itself does not vanish at 0 and it does not vanish at pi. Because if it vanishes there, this thing blows up. Because you have 1/0 in here. Okay. So if you make those conditions, you will find that this term in here better be canceling at those values, namely at most ML is equal to ±L. So now you have another condition in L. I mean ML and L. Okay. The last condition comes from this term in here. This solution also will blow up exponentially unless you terminate the expansion at some values. And those values actually correspond to, because you have an L in here too, at L equals to n-1. So the last condition is L at most is equal to n-1. It could be n-2 if you like, and so on and so forth, up to L equals to 0. So L is a positive integer from 0 to n-1. So that the polynomial expansion here at the end will cancel the growing exponential, and at the end the solution will be finite. Remember, the particle must exist somewhere. The total integral of psi must be finite. So this is in a nutshell how the solution proceeds. So these are the 3 quantum numbers that pop up off of this for the hydrogen atom. That you have an n that is an integer in such a way that the energy is equal to negative 13.60 electron volt divided by n squared, and another quantum number that you're free to choose between 0, 1, all the way to n-1. That's it. And then for each value of L, you have choices for the quantum number ML, which can be, in this case, if you choose 0, it's 0. For this one, you have 3 choices, 0 or ±1. For 2, you will have 5 choices, 0, ±1, or +or-2, and so on and so forth. All the way to here, of course, you will have a bunch of choices, 0, ±1, +or-2, +or-3, all the way to +or-n-1. Okay, so this is basically the solution that you end up with. Okay. How can you? Because let me take you a little bit historically. The Siemens effect was known to scientists when Mr. Bohr came up with a model of the hydrogen atom, and he was able to explain, for example, those transitions to the L equals to 2, because that's the easiest one to see because of the n equals to 2. I'm sorry, because of the fact that you have those are in the visible range. So if you have the spectrum, this is n equals to 3, this is n equals to 4, and this is n equals to 5, and so on and so forth, okay, according to his calculations. So this will be probably in the red light. This probably will be the yellow, or the middle. It's kind of a bluish, greenish thing. Okay, and this will be the blue, okay? So you can see this lines clearly. However, in the presence of a magnetic field, inside a magnetic field, these lines appear to be split Okay. These lines appear to be too many. This is how the red probably is going to break down. And this is how the other spectrum breaks down and the other one. So there were splitting, and you can find the splitting easily with the fine grading. You take this diffraction grading and make sure it's fine and use it there. And then all of a sudden you're detecting small variations on those colors. Mr. Bohr's model cannot explain that. It's impossible for his theory because there is nothing. I mean, the calculations just take the energy in this level, which is negative 13.6 divided by 9, and this is negative 13.6 divided by 4, and then take the difference of the energies, and that gives you the frequency. Remember, the energy is hc over lambda, and that's basically gives you the value of lambda, the different wavelengths that you're supposed to find. And you will find only a unique wavelength. You're not going to find 3. You're not going to find 3 here. You're not going to find 3 in here. So Bohr's model failed. I mean, it was able to explain the main spectral lines, which is very good, but there are some fine structure in there that we couldn't see, we could not explain based on his number. Okay, so look at the energy in here. It does not depend on L and M, so it's really degenerate. Meaning, for different values of L, you can have as all of the energies are the same. Meaning, for 3 in here, for n equals to 3, you're looking at. Let me look at the n equals to 3, for example. N equals to 3, L can be 0 or 1 or 2. Remember, we stop at n minus 1. ML also can be 0 in here. In this case, you have plus or minus 1 and 0. And in here, you have plus or minus 2, plus or minus 1 or 0. So you have a total of, let's count them. You have 5 here possibilities, plus a 3, plus 1, that's 9. 9 different quantum choices for your L and M, L and ML, all corresponding to the same value of 3. The same energy, basically, which is negative 13.6 divided by 9. It's the same value. All of them have the same energy. So you have 9 potential states. Please don't remember this because it's not actually 9, it's more. It's 18. Okay? And we'll see why. So you have this many states in here potentially in that level alone. In n equals to 2, obviously you will have less because of the fact that n equals to 2 will only have L equals to 0 and L equals to 1. So in this case, you will only have 4. Okay. But again, I was saying in here, you have to multiply that number by 2 because you're going to end up with 8 actually. Okay. So you have degeneracy of at least 9. And now we know because of the spin, actually, each electron will have either an up or down spin. So in this case, you could have up to 18, not 9. Okay. So in this case, the degeneracy is, according to this model, up to this point is 4. But in actuality, it should be 8. Okay, and that is all corresponding to the same energy level, negative 13 over 6 divided by 4, which is 2 squared in this case. Okay, so it seems like similar to what happened in our box earlier of dimensions L. When we removed the symmetry in it, then we lost the degeneracy. Then the energy levels became different. So it seems like in this situation, there was a degeneracy in here, which is this one, but somehow it was lifted. It was removed in the presence of the magnetic field. So in an attempt to understand that, so the Siemens effect, which was known in 1896, way before the Niels Bohr's model, okay? So it was nagging because it was minor corrections. Of course, you need a fine diffraction grading to find it, but you can find it. It was not hard to do. Actually, as a matter of fact, there is an anomalous Siemens effect that we're going to talk about that actually also was going on in the same time. When you look at the spectral lines, for example, coming from the sun, they all look beautiful for the most part, except those that are coming from the dark regions of the sun, you know, the spots, the dark spots in the sun. Those where there is an intense magnetic field going on in there, those lines appear to be split, according to the Siemens effect. Okay, so that's really the trigger for that. So if you consistently look into the dark spots on the sun where the magnetic field is strong in there, the hydrogen lines, which you can study, are split. So they are not according to this theory. Somehow the magnetic field will lift the degeneracy. So how is we can understand it? Okay, here is what we think, okay, going on in this case. Okay, the electron, as it moves around the nucleus, the electron, of course, is a negative charge. So if it's going clockwise, it's equivalent to a current going counterclockwise, I. Okay, so that's basically what's going on. So it's a current going around that circle. And how do I find the current? It's easy. The current, I know I gave you the full derivation for how the angular momentum is related to ML, and I posted it as a PDF file. So hopefully, guys, you will have a chance to go through the whole derivation. It's going through those same basically spherical coordinates and how to convert the different kind of partial derivatives in order to arrive at the result. Okay, so that's because in the book, and I refer to that in the notes in there too. The book gives you just a formula at the end, which is equation. I'm trying to find it. Okay, 4135 or something. No, 4133 and 4135. All of these equations, they are actually connecting the angular momentum to ML, because it assumes that somehow you can find it. Okay, so this is basically the theory behind it. If you guys remember, so the current in here, first of all, is equal to the charge, or the rate at which the charge moves with respect to time. Well, that's it. That's what the current is. Okay, if you guys remember from your physics 2 class, that the moment, the magnetic moment, magnetic dipole moment, mu, which is a vector normally, is IA. You remember this from your physics 2 class?
Yes.
Okay, very good. So it's just the current times the area. I'm going to take the magnitude of this one because I know I'm taking this in coordinates in such a way that this is in the z-axis. Okay. Obviously, the actual moment is going to be negative at the end because of this. If the electron is were to go clockwise, like this one, in other words, it has an angular momentum positive, greater than 0, spinning like this, then its mu is going to be pointing down because of the fact that I'm dealing with a negative charge. That's all. Okay. So, so in this case, the current again is going to be. I'm going to take the magnitude only. Okay. So I'm not caring right now about the sign. Okay. So it's going to be the charge divided by the time it takes for the charge to go once around the nucleus. And the time for it to go once around the nucleus is the circumference, which is 2 pi r, divided by the velocity. So whatever velocity it has, this is the value that it has in there. Okay. So this is the time it takes for it to go once around the circle. By the way, the area in this case is this area, which is just pi r squared. Okay. So having said that, that gives me then mu in magnitude equals to, first of all, this ratio, which is EV divided by 2 pi r times the area, which is pi r squared. Cancel the r with the r, cancel the pi with the pi. And at the end, I will find the mu equals to EV divided by times r divided by 2. Here is also what I know from physics 1. Do you guys remember this result? From physics 1, the angular momentum and the linear momentum and how they're related for a point particle. Yes. It's the cross product. So if you have a point particle moving with the velocity mv, and this is the radius r. And from the center of rotation, from the center of rotation, so this is my center of rotation, okay? So in this case, it's just a cross product of r times the momentum. So it's going to be r times mv times the sine of this angle theta. This is actually the foundation of the angular momentum. This is the how we defined it actually in physics 1. This is the starting point for the angular momentum. Obviously, if you have a bunch of particles in physics 1, m1, m2, m3, and so on and so forth, a bunch of them, and you have a center of rotation somewhere, then you're going to calculate this value in here. Okay, so it's going to end up being, in this case, R1 time crossed with P1, and also R2 crossed with P2, and so on and so forth. Okay, so when you add up these numbers, here is what's going to happen in this case. Okay, we're going to take the easy case where it's a rigid body. When it's a rigid body, actually, and it's the center of rotation in here, when it's a rigid body, that means the distances do not change. They are fixed. That's what the rigid body is. Liquid, for example, is not rigid. Okay, so in this case, these distances are the same, and all the particles are moving with the same angular velocity with respect to the center of rotation. So all of their velocities in this case, the VIs, I'm going to call them, are the different m's times the different ri's of how far that particle is times the same omega, because a rigid body will move with the same angular velocity omega. Otherwise, if parts of it move with the higher omega than the other part, the rigid body starts to become non-rigid anymore. It starts to break apart. Okay, so I'm trying to refresh your minds for this, what this relationship, how is it, because it's going to ring a bell the minute I write it down. So at the end, this cross product, because the angular momentum is going to be perpendicular to the plane where the rigid body is moving. So at the end of the product, there is no sine theta in here. It's going to disappear. So we'll have an Ri for the first particle, R1 times M1. They have different masses probably too. The M1 times R1 omega plus M2 times, no, let's put the same order, R2 times M2 R2 omega, because the velocity in this case is going to be just R omega. It's just the velocity of a particle going on a circle. Okay, so at the end of the day, the omega is the same, so it's going to come out, and all I'm doing in here is summing through all of my different mi's, the little masses M1, M2, M3, and so on and so forth, and with the distances R1, R2 squared, okay, Ri squared, and this is L. This is, or what did you use for it? No, this is I. I'm sorry, the moment of inertia, I. Okay. As a matter of fact, when you have too many points in here, the sum becomes an integral, and it becomes the sum of the dm times r squared times omega. So this becomes I omega, and that is L. Does this now remind you of something from physics 1? Yes.
I can't remember that far back.
I mean, I recognize it now, like a little bit, but like, yeah, same Maddie.
Okay, yeah, I omega at the end, that's what you use because you're assuming that the rigid body is rigid enough so that the distances do not change. If they change, then you have a problem. It's not rigid anymore. That's what allows you to pull the omega out, and then that summation becomes this summation is throughout the entire rigid body. Okay. But each and every one of these particles actually is a point particle whose angular momentum is just r cross p. And r cross p at the end of the day is going to be this term, r times m1 times r, and so on and so forth for each different particle, because I'm assuming that they don't probably have the same masses. As a matter of fact, when I take a rigid body, if the distribution of the mass is uniform, then I'm going to put a rho times dv in this case if it's a volume, or sigma times ds, dx dy if it's a plane. I mean, it's on a plane, like a thin body, or if it's a one-dimensional, I call it lambda dx, and then at times the x squared in that case. Okay. Did you do calculations for the angular moment? You did for the moment of inertia. for the different, for the rod, I think it's what, like 1/12 times ml squared, where L is the length of this one. This is with respect to this end. And the sphere was something 2/5 mr squared. And for the disk, it was something like 1/2 of mr squared. Do you guys remember this calculations or not from your physics 1? Yes. It's ancient, isn't it?
It is ancient.
Okay. Look, this is how we get the angular momentum. So the magnitude of the angular momentum for my case problem in this case, since I'm assuming that the angle phi is along the xy plane, and I'm concerned only with the z direction. So the z component of this one is just going to be whatever the particle is, which is r, crossed with its mv, which is the linear momentum. And in magnitude, I'm assuming it's a circular path in this case because of the symmetry. Okay. So there will be no sign of phi, because the tangent in this case and the normal on a sphere, they make a 90-degree angle. So r is here, and mv is here, and this is a 90-degree angle. So if I do the dot product, I mean the cross product, it's r times the momentum p times the sine of 90 degrees, which is 1. Okay. So at the end, I will get r times p, the magnitude in the z direction. So Lz, that's what I'm concerned with. So Lz is going to be basically equal to, Lz is going to be for this particle is going to be r times mv. Make sense, at least through this formula, what it should be? Yes? Guys, is it yes or no?
Yes, it makes sense.
Okay, because again, r, the magnitude of r is r, the magnitude of p is mv, and the sine of the 90-degree angle is 1. So it should be correct. Okay, so I'm going to go back to this expression that I was trying to finish in here. For mu, for the magnetic dipole moment, mu, I found it to be equal to EVR divided by 2. So it's E times V times R divided by 2. With the exception of an M that I'm missing in this expression, I have R times V, and here is R times V, but I'm missing an M. So if I multiply and divide by M, I'm in business. This is nothing but LZ. So this is E LZ divided by 2M, where M is the mass of the electron and E its charge. In LZ, if you guys remember from my discussion up there, or actually from the PDF file that I posted for you guys, LZ turned out to be exactly related to ML. LZ is going to be equal to ML H bar. Okay, it's a lengthy derivation. It's, I think, a page and something. And then there are some steps that I'm hoping that you guys will fill the gap, because I summarized some of the calculations and I made the cancellation quickly without going through them, because I can see clearly that they cancel. And if you don't see them, please let me know. At the end, LZ will turn out to be, as an operation, is just the H bar over I times the derivative with respect to phi. And the derivative with respect to phi is exactly the function phi is that exponential of IML phi. So if you take that derivative, the I cancels the I, and the ML drops down when you take the derivative, and the function itself stays the same, and you pick up an H bar in here. So the measurement for LZ is going to give me then the magnetic dipole moment in this case is going to be for the electron EH bar over 2M times ML. And here is the wisdom from using L as an index to indicate that this is an integer as opposed to the mass of the electron in here. That's all, to make that distinction. A lot of quantum mechanics books and a lot of actually the textbooks also, they don't make this distinction, assuming that you know what you're talking about. Each m is different than the other m. One of them is the mass of the electron that goes in here, and the other one is the quantum number m. Okay, so there is that thing in there. That's why this quantum number is called the magnetic quantum number, because of what is going to happen next. Because if I take this atom in here and put it inside a magnetic field B, then in this case, I will have, obviously, I really need to add the minus sign now because of the fact that this is a vector now, so I have to worry about directions. So it's going to be minus mu dotted with, so this is how much the energy is. So if you take a dipole magnetic moment, dipole magnet, for example, and you put it inside another magnet, it's going to turn, okay? And the torque with which is going to turn will correspond to an energy, and that energy of interaction is just the minus the product of mu times b, okay? So if there is a cosine between them, it's going to align itself with it. That's exactly what happened with a regular magnet. And that's exactly what's going on in this case. So the mere fact that those atoms are actually inside the magnetic field, whether in the sun or in the laboratory, then in this case, the energies, they are going to be broken down. So I'm no longer going to have 9 states all piled up in the same state, but I'm going to have them separate. Because the magnetic field will react to each and every one of them mu's. Okay, each one of them has a different mu. Okay, so this is basically what's going to happen. This is what the splitting is coming from. Obviously, this number in here usually is written differently than what I wrote it. The mu is equal to negative ml times mu b, where mu b is called the Bohr magneton. So it's mu b is equal to, by definition, E h bar over 2 ml. So you have all the numbers. H bar is 6.626 divided by 2 pi times 10 to the negative 34. E, which is 1.6 times 10 to the negative 19. Usually you don't write E in this situation because you want to express everything in terms of electron volts, okay? So if you do that, then you can express in terms of the electron volts. Otherwise, 1.6 10 to the negative 19 divided by 2 times the mass of the electron, which is 9.109 times 10 to the negative 31. And if you do the algebra, you're going to find the value of mu b, which I really don't memorize. Okay, so in electron volts, mu b, so the Bohr magneton, so this is the Bohr magneton. Mu b is equal to, because all of these numbers are known. Okay, so it's 5.788 times 10 to the negative 5 electron volt per Tesla. You see in here, 1 Tesla of magnetic field will cause a tiny shift in the energy. 1 Tesla is a big magnetic field, by the way. Okay. So in the laboratory, if you manage to have 5 Tesla or 2 Tesla or even 0.4 Tesla, you should see significant shift in the energy levels. Okay. Although 13.6, for example, for n equals to 1, there is no, for n equals to 3, how much n is equal to 3? It's negative 13.6 divided by 9, which is roughly about 1 point something. Okay. So 1 point something electron volt compared, even if you bring it to 1 Tesla magnetic field, it's going to be a correction of several decimal points before you get into it, okay? You guys understand that this is a minor correction? That's why in the spectral analysis, those shifts, you really need to have a fine measurements to find it. Obviously, there is another expression that we sometimes need, and that is one in the joules. So it's going to be 9.274 times 10 to the negative 24 joules per Tesla. Okay. Obviously, also another convenient unit so that you guys remember for the magnetic, for the dipole magnetic moment, because it's a current. What is a current? Current times area, and the current is amperes and area in meters squared. Because these units are in SI, this is also another way of expressing it in terms of ampere meter squared. So those are equivalent. Okay, both of them are equivalent. So, but it's not this number in here. This is, you have to make it in a different unit system in there. So there is, they use different units for the charge and the so this is the value in ampere meter squared. Okay, so this is basically the splitting of the energy levels. Okay, and how we see them. Now here is something of interest to us. Let me explain. Okay, I'm going to take the same example as the book in here. Okay, between the 3D level and the 2P level, the 3D level and the 2P level. So the 2P level in here, that means n is equal to 2, and this is n equals to 3. This is the red light of the hydrogen atom. Okay, that is the one that is going to be split in this case. So in here, for the 2P level, as I was saying before, you have okay, one thing about the notations I forgot to mention. When L is equal to 0, this is a symmetrical solution, and it's called the S state. Okay, when L is equal to 1, this is the same thing as saying P state. In this case, actually, it's there is some symmetry, and the symmetry is actually not spherical. So this is spherical symmetry, but in here it's a little bit lost at spherical symmetry in this case. L equals to 2 is the d orbital. Okay, L equals to 3 Spdf orbital, and so on and so forth. So when you see a letter in here, P, you know the value of L is equal to 1. When you see the value of D, you know the value of L is equal to 2. Okay, this index in here, 3, represents the energy level N, the principal quantum number N. Okay, so in this case, we have a transition from n equals to 2, n equals to 3, I'm sorry, to n equals to 1. So there is an emission in this case spectrum. So we want to understand the splitting of the hydrogen atom. Of course, L is equal to 1. So ML in this situation can be equal to -1 or 0 or 1. If there was no magnetic field, it's all the same value. All of them are identically the same value, namely E2, which is equal to -13.6 divided by 4. Okay. However, in the presence of a magnetic field, I need to add a mu b times the B magnetic field to it, and subtract a mu b divided by the same value. Here is the thing. So this is the energy shift in this case, is going to be equal to minus or plus, depending on the value. It's going to be just the interaction of these two. Okay, one thing. You have a negative sign in here because of the potential energy being negative in this case, because of the sign when you do integrate it, that the preference of a magnet is really to align itself with the external with the dipole with the external magnetic field, and that is why the negative sign is in here. Okay, and the mu b itself has mu itself has a negative sign already. So when you do the algebra, it's a negative times negative, so it's going to be a positive. So delta U is just positive in this case. ML times mu BB. Okay, so that is the final value for the energy shift in this case. Okay, so let's look at this situation in here. In this situation, I have a -13.6 over 4. I add to it ML in this situation. For ML equal to 0, I don't add anything. So the value in between stays the same. So the energy is not shifted upward or downward. For ML equals to -1, I'm going to shift it downward. And for ML equals to 2, I'm going to shift +1, I'm going to shift it upward. So in other words, when in the presence of the magnetic field, this same energy level now is 3 different energy levels, separated by this amount, mu BB, because ML is 1 now. So there is a mu BB here, and there is a mu BB here, negative mu BB if you wish here. Okay. Now this one is a different story. I have L equals to 2, because D is L equals to 2. And then ML can be 5 values. ML can be equal to -2, -1, 0, 1, and 2. Okay, the 0 stays the same because all I'm doing is multiplying 0 by this number, so it's going to be the same. So this is ML equals to 0 level. Okay, so that is not shifted. But I add, for the first one, I either add 1 or subtract 1. So I'll have 1 shifted up and 1 shifted down by mu BB. And then I have 2 also mu BB and -2 mu BB. So this energy level in here is shifted by 2 quantities in here. Okay. So for this transition, I have potentially so many transitions in here possible. And I'm going to write it down, the allowed transitions, and I will tell you why they are the allowed transitions. Okay. From 2, let's say this is -2. This is -1. This is the ML. I'm following the ML, okay? This is 0, ML equals to 0. This is ML equals to 1, and this is ML equals to 2. This one is ML equals to -1, 0, and 1, okay? I cannot go from -2, or I can go from -2 to -1 because there is an addition of 1 value. So in this case, this is allowed for ML. So this transition is possible, okay? Delta L is possible. Delta L has to be 1, okay? In this case, it's possible. So there is a change in, and I'm going to explain where these things are coming from. So in this case, from -2 to -1, I have shifted by 1 value, okay? From -2 to 0 is not possible to shift ML by, so these are the requirements, and I'm going to explain where these things are coming from. Either a 0 amount or plus or minus 1. So going from -1 to from -2 to -1, that is actually a +1. So that is allowed according to this rule, okay? And these are called the selection rules. So this is fine. But I cannot go from -2 to 0 because that amounts to adding 2, and that is not allowed according to the selection rule. I cannot go from -2 to +1 because that means I add 3, and that is not allowed. So the only transition from this energy level, now that is the degeneracy is gone, up to this energy level is here. Okay, so that is the only acceptable one. Now from -1, obviously I cannot go to -1 also. I cannot go all the way here because that, I'm sorry, from -1 to -1 is acceptable. What am I talking about? So that is good because the delta ML is equal to 0 in this case. So this is acceptable. From -1 to 0, that is also acceptable. That means I'm adding 1. Okay. But the point I'm trying to argue in here, from -1 to +1, that is also not acceptable. That means I have to add 2 to this ML number. Okay. From 0, from this one, I can go to any of those numbers. I can go here. That's ML equal to 0. I can go here. That means I went by I subtracted 1. And from here, that means I added 1. So all of these 3 are acceptable. Now for 1, from 1, I can go to 1. There is no problem with it. And I also can go to 0. I cannot go to the other one because that would amount going from 1 to -1, again, subtracting 2. And that is not acceptable according to this rule. The last one is from 2, I cannot go to 0 because that means that I have to subtract 2. I cannot go to -1 because that's going to be subtracting 3, but I definitely can go to this one, which is at the end of the day, subtracting 1 from ML equals to 2 to ML equals to 1. So at the end of the day, not all possible transitions are acceptable. The only ones that are acceptable are the ones that conserve the angular momentum. because the outgoing photon will carry with it an angular momentum. The photon that is emitted will carry with it an angular momentum. So how was the angular momentum is carried? If you guys remember from physics 2, an electromagnetic wave, which is the photon that is leaving, actually can be polarized, and that polarization can be a circular polarization, can be either left-handed or right-handed. It can be either positive or negative. Okay. So in this case, I already have a value in here for L. And I can have a value for it for 0, meaning that in this case it's going to retain the value that I got from L. Or it's going to flip it and be polarized in the opposite direction. At the end of the day, the selection rules are coming from this ones in here. Okay, the selection rules are going to be a little bit complicated, but it's actually easy to remember them as follows. Delta L has to be positive or -1. -1 is for the absorption, and +1 is for the emission. And delta M, in this case, can be 0 or ±1. That is not the full story, though. If you do a calculation for the energies, because the energy in this level is going to be E3 is going to be whatever it was before, which was -13.6 divided by 9, plus, if I'm interested in this calculation, for example, from here to here, plus in this case, I have to subtract this value from it, which is going to be, what is the negative value in here? So this is negative 2 mu b, and then I have to find the value that corresponds to this value, which is E2, and E2 is going to be -13.6 divided by 4 minus mu bb. The point I'm trying to say, at the end of the day, you're going to find the difference between the two energies in order to find lambda, hc over lambda. So hc over lambda would become just E2 minus E3 divided, this is the energy, is equal to hc over lambda to find the corresponding lambda for it. Okay. Obviously, you're going to find one value that is different than the value if you really did not have a magnetic field in here. Okay. So it's going to be shifted by a value of minus mu b minus -2 mu b. So it's going to be added to it, a mu b to it. Okay. If you continue with the same calculations, you will only have 3 different spectral lines. In other words, if I'm going from this one to here, from -1 to -1, at the end of the day, I will have no split. So this will be different. From -1 to 0, it's going to be shifted on the other side. And in here, they're going to be the same values. In other words, you will have only 3. Do you want me to guys to go in the details, or do you guys see that there should be only 3? I mean, it looks like I have a bunch now. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 different kind of acceptable values, and they are all 9 acceptable values. Okay, there are some that have been rejected by the selection rules, but there are the one that even they are accepted, they break down at the end into 3 different values, because you only are shifting by a certain value. At the end of the day, you're either adding a mu b, or you're subtracting mu b, or you're canceling the mu b altogether. So at the end of the day, the actual spectral line before the magnetic field is only 1 line on the spectrum. Now it should look like 3 lines on the spectrum. And the separation in here, in wavelength, of course, you're going to calculate delta lambda, and the delta lambda should correspond to different values that you either add or subtract for mu b times b. Okay, so again, you will have some problems, I promise that you will, that will go in detail about how to find this one. 2 things in here of importance. First of all, degeneracy is lifted because of the magnetic field, and Schrödinger's equation now explains perfectly the Siemens effect if we follow its steps in here, because that should be observable, and it was. Okay, so this was good. Make sense, guys? Okay, very good. So basically, as long as you follow the calculations, you are, as I was saying, you will only see separation here. What I was talking about in here, once you find E2, you subtract from it E3. This should give you delta E. This should correspond to the emitted frequency or wavelength, because most of the time we deal with the wavelength. Obviously, when you calculate lambda in this case, before the magnetic field, so it's all the three, they're all the same value. So this value is not going to be there at all. So it's only going to be one value for lambda. And that was this one. Now, in the presence of the magnetic field, some of them will be shifted by plus mu b, and some of them will be shifted by negative mu b. Mu bb, that's the times the magnetic field, don't forget that. And at the end of the day, this difference in here will be slightly off, either one side or the other side, or sometimes it doesn't shift at all. Even in this calculation, it doesn't shift at all. As you can clearly see, for example, from the case of -1 and -1. Okay, so this should not shift. It should remain the same old value that you had before. Okay, so in this case, you will have 3 spectral lines near the spectral line where you are. Obviously, this shift is so small in lambda, because remember, the value of mu b is tiny. Even in the presence of a strong magnetic field, this value is still a small one. So at the end of the day, this is how the Zeeman effect can be explained. Good. Everyone else other than Cameron?
I said good.
Okay, very good. So now here is, as I was saying, there was another nagging issue came there, namely the anomalous Zeeman effects. Okay, so there was another one that was going on at the same time, and that was a problem. How do you spell anomalous in here? Yeah, I know. With a refined version of this thing, it seems like there is even finer splitting of the spectral lines. Quantum mechanics did not find an answer for it. Okay, until Mr. Stern and Gerlach, they were doing an experiment. Basically, they took different metals, and they took them through a non-uniform magnetic field, basically that has this kind of shape in here, distributed in space. So you have a magnet in here. Okay. And in the bottom, you have a regular magnet. So one of them is a North Pole, the other one is a South Pole. So if you send a bunch of neutral metals in here, you expect the L, the ML, actually to respond to the magnetic field, and you will have a distribution more or less uniform in this case, depending on the ML of the outer electrons. In this case, you will have 2 L plus 1 divisions. Okay. Remember, L is an integer. So let's say, for example, L equal to 3 or 5. So you'll have a bunch of them. So there should be a distribution on the screen in here of the particles as they are interacting with the magnetic field, okay, depending on ML. Okay. Okay. So that was really the solution they expected for some materials, not all of them. Okay. Where the conditions were the right ones. They saw the splitting of these lines into just 2, where in this case, ML is supposed to be either canceling or 0. So there appears to be an additional property that was not accounted for. Okay, that appears to be actually splitting the spectrum in 2. As a matter of fact, if you think maybe if I reorient it differently, as long as it's the same sample, is going to get the same, even if you orient it slightly differently. So this is the Stern and Gerlach experiment. So here is the proposal then. It seems like there is another angular momentum, intrinsic angular momentum, that satisfy this equation, except I have to multiply it by half integer to get the splitting in 2. So 2 times 1/2 is 1 plus 1 is 2. So now it seems like that's how this splitting is happening if I require that this angular momentum is exactly 1/2. Okay. So if the angular momentum is exactly 1/2, it seems like it's working. And this is intrinsic because everything is canceling. So at the end of the day, so where is this thing is coming from? It's an intrinsic property. So what's his name? I forgot the names. The two people from Holland. Basically, they gave it the name of a spin. Okay. Somebody asks you what is the spin of an electron. So the spin can be a positive 1/2 or a negative 1/2, and the of course h bar. All of these things are multiples of h bar. Okay. And so if somebody asks you what is the spin, I'm going to give you the answer, okay? In quantum mechanics, of course. So imagine this is what they said, okay, and this is what the book says, okay? You have to be careful with this thing. Imagine the Earth going around the sun. So you have the sun in here, and you have the Earth in here. Okay. As the Earth goes around the sun, it has an angular momentum that is equal to r from the distance from the Earth to the sun, crossed with p, which is the linear momentum of the Earth as it revolves around the sun. So this is p, and that is r, and you do the cross product, and this is the orbital angular momentum. So this is the orbital angular momentum, just as we calculated earlier. Okay. Add to it the spin of the Earth around its own axis. So imagine the electron is a sphere, and it has an internal motion, in this case, around some axis. That internal motion, if you have a charge distribution in here, dq, okay, so that when you add this dq over the entire sphere, it gives you the charge of the electron E, okay, and it's spinning. So it's spinning around its own axis, and as it spins, I'm going to find the different values of the spin, if you wish, the angular momentum in this. Remember, in this case, the interangular moment turned out to be quantized, and the magnetic moment turned out to be proportional to, angular momentum turned out to be proportional to this LZ, okay? So in this case, in a similar fashion, I can find the angular momentum associated with this motion, call it S if you like, and at the end of the day, once you find the S, you're going to find the magnetic moment due to the spin, which is going to be some sort of a value that has to do with this S times the spin value times, again, SZ, okay? So this has to do with the Z component. So in other words, I can project this in the SZ direction and find a different value. Here is where this is, the similarity ends, okay? First of all, you guys understand the picture or not? So what I'm saying in here is that as if the electron is an Earth spinning around its own axis, so I can find its angular momentum. Once I find its angular momentum, I use the same trick as before, multiply that angular momentum by the quantum number that is appearing in here, 1/2, and then I'm in business. Make sense?
Yeah.
Yep.
Except I really don't have the sun and the Earth, and I really don't have a spinning electron, and I really don't have an angular momentum calculated this way. Everything else I said is correct. This picture is wrong. In other words, this picture is not true. Everything else I said is correct. Make sense? Or did I confuse you?
Yeah, makes sense.
This whole picture is wrong, so that you guys understand. There is no counterpart there is no classical interpretation of a spin. The spin is a quantum mechanical property, pure quantum mechanical property. So technically, we always say, okay, listen, imagine you have a sphere, okay? This is a textbook example. Imagine you have a sphere, and this sphere is spinning around its own axis, so it has an angular momentum. That angular momentum is quantized in the same fashion as the orbital angular momentum was quantized. And now you have a moment of a magnetic dipole moment. This whole thing is not correct. This whole thing is not true, because I really don't, the electron is a point particle, it doesn't have size. So it does not have physical size, it doesn't have center of mass. And even if this picture is somehow acceptable, because somehow you can find the charge as it's moving, spinning around the axis, and then somehow you compute a value for it. What happened to the neutron? The neutron has no charge, yet it has a spin, the same value actually too. It's a spin half particle too. So this model is completely not correct at all, and it won't work in quantum mechanics. So, I mean, it's called spin, and sometimes the image is giving that this is like some sort of a sphere spinning, but that is not true. This is not correct at all. Okay. And my screen went blank. Okay, we still have a long way, actually, honestly, to finish this this chapter. So we have a break for about 15 minutes, and then we come back. We're going to find the coupling that explains the phenomenon that I'm talking about. Okay, the secondary or the anomalous Siemens effect. And then we will discuss the periodic table. We should have a full understanding of the periodic table and how it looks like, okay? Because once we introduce the spin, then we're going to argue for the Pauli principle, Pauli exclusion principle. Then we'll have a full understanding of the periodic table. We finish it with the X-ray spectra and the entanglement. So that's the unit for you guys. So we're going to finish this one. The exam, by the way, and I did not mention that in the beginning because there were not too many of you, is now scheduled for April 14th. Not this coming Thursday, but the Thursday after, okay? Make sense? Okay.
Yeah.
So I'm gonna pause. I'm not gonna leave, so I'm gonna pause the recording, and I'm also going to pause the video and the sound so that you guys can go and drink something and come back, and we'll finish as much as we can, and then we will see each other next time. Okay? Sounds good?
Yep.
Okay, so I'm gonna pause the recording. Again, welcome to part 2 of this basically long chapter, really. Okay, there are so many ideas in it. So we ended up with talking about the spin, and there was some experimental evidence for it actually, and those experimental evidence led us to come up with a new basically quantum number. So in addition to NL and ML, now we have S also to worry about. Okay, so now we have 4 quantum numbers that we have to include in our analysis altogether. I have several points in here to talk about. First of all, question in the pretest that we really need to address right now and now. And the second thing is the introduction or the theory behind it actually of the spin. Okay, it turns out that it's actually a relativistic value. It's coming from relativity when Mr. Dirac actually tried to require that Schrodinger's equation really meets the symmetries in the problem. One of them actually has to be Lorentz invariant and the Lorentz transformation. So invariant in the Lorentz transformation, and also in the rotations and also in their translations. So when he did that, one of the solutions actually was clearly pointing to a value for particles moving past in time basically backward in time. And that solution, or negative energy, so when that solution was rethought in terms of the symmetries in the problem, it turns out to have the correct value for the spin. So that is where that value actually emerged from. So at that point, he came up with the theory behind it. But again, it's a quantum mechanical value, so there is no counterpart for it in classical mechanics. Problem 59 from the end of the book basically gives you a hypothetical scenario for another universe, not our own universe, where the electrons in that universe happen to have a value also of 3/2, because that should also work in a Stern-Gerlach experiment, because then in that case, you will have integer values. When you 3 times half times 2, that's 3 plus 1, so you'll end up with 4 actually. So in that case, the universe, it's wondering what happened in that universe in terms of the periodic table. You will see that the periodic table shifts drastically. For example, the helium atom will no longer be inert gas. It's going to, basically the periodic table shifts completely. Okay, beryllium actually becomes inert. So the whole elements shift completely in that case. So the fact that we have the spin equal to 1/2 is actually this universe where we are in right now. Okay, so it's this situation. So let me share the screen so that to discuss an important point related to the pretest question, and then we continue with our discussion. So remember, now we have 4 quantum numbers. Let me use the normal pen. We have n. This is the principal quantum number. Which is an integer, and it can be values of 1, 2, and so on and so forth, okay? All the possible values that you have. This is the hydrogen atom. We're still dealing with the hydrogen atom. L, which is the orbital angular momentum number, if you want to call it, okay, is equal to, again, from 0, 1, all the way to n minus 1. So there is a cap on it, and it's coming from there. So this is the angular momentum. Quantum number. The third one that we saw already coming from the solution of the equation is ML. Again, this has values depending on L actually. It can have values of 0, positive or negative 1, positive or negative 2, up to positive or negative L. So this is capped in there. In addition to that, now we have the spin. So the spin is also, so this is the magnetic quantum number. And the reason why it's called magnetic is when you apply magnetic field, this is the one that comes into the magnetic interaction. So it's called the magnetic quantum number. And this is really has to do with the projection of the angular momentum. So this is the magnitude of the angular momentum actually is L square root of L times L plus 1 times h bar, okay? So this is the magnitude of the angular momentum altogether. So if L is equal to any value in here, 1, for example, if L is equal to 1, the actual L, the angular momentum magnitude as a vector is square root of 1 times 1 plus 1 times h bar, or square root of 1.41 h bar. So this is the actual magnitude of the angular momentum itself, okay? So the quantum number tells you how big that number is, that's all. So it's not directly, and it's an integer, as you can clearly see, little l. But big L is the whole vector. Okay, obviously in that scenario, for this same case, ML are the projections of the vector along the z-axis. So ML, in this case, is related to the z component of the angular momentum. So it's ML h bar. So in other words, if I go back into my original example in here of L equals to 1, for L equals to 1, then in this case, I have 3 possibilities for ML. Either 0 component, this is 1.41 h bar. Either 0 component along the z-axis, and that corresponds to ML equals to 0. There is no component. So this is still my z-axis, okay? My z-axis is along this direction. So this vector has no component. So L is still there, but ML in this case is 0. And remember, the function depends on I ML phi. So if ML is equal to 0, that means this function doesn't depend on phi at all. It's symmetrical with respect to the ring. So that means the function has the same value all over the circle. That's all. It's uniform. Depends on theta, depends on because L is 1, so it depends on theta, and it depends also probably on N2, depending on which energy level we're talking about. But phi, as far as concerned, because you have cosine of 0, which is 1, okay? Sine of 0, which is 1, so that's which is 0, but that's a combination of the two. So E of 0 is 1. So this is going to be 1. So whatever normalization factor is going to go there, and that's it. So it doesn't depend on phi. But then you have two other values. So this is ML equals to 0. You also have ML could be +1 or -1. So there is 1 in here that corresponds to this projection of the same value, 1.41 h bar, and negative value that corresponds to, so this corresponds to ML equals to -1, and this corresponds to ML equals to 1. So how much this angle is? That should be 45 degrees. Why? And I will tell you why that is. Because this angle theta is equal to, so this is the projection in the LZ direction. So LZ is equal to ML times h bar. So this is h bar. And this angle theta, cosine of theta, for example, is equal to h bar, the adjacent, over the hypotenuse. Remember, the length of the vector L is determined. It's just the square root of L times L plus 1. So in this case, is 1.41, square root of 2. So divided by that square root of 2 times h bar. And this is equal to 1 over square root of 2. So that means theta in this case is 45 degrees. So this is what was going on in here. We can determine L by just using this expression. And ML now will have different values in here. ML will have times h bar, I'm sorry. ML in this case, or the z component of the angular momentum, actually will be 0 plus or minus 1 all the way to plus or minus ML plus or minus L times h bar. Each and every one of them is times h bar. So this is what's going on in terms of the angular momentum. Here is something very important to remember. You cannot know what Lx is and what Ly is. Period. So if you're wondering where is the x component of the angular momentum and what is the y component of the angular momentum, they don't exist. I mean, it's not they don't exist. You cannot know them. And that is because of the Heisenberg uncertainty relationship. If, because of the rotations around the axis, and that's where the angular momenta are coming from, the rotations. Rotations are not, you cannot permute them. You cannot, if you rotate around one axis and then rotate another axis, you cannot rotate first around the second axis and the first axis. So this is one of the properties of rotations. So in other words, I cannot know Lx, Ly, and Lz in the same time. There is an uncertainty about that. So the only thing I can know is one of them. Usually, we choose it to be Lz. So if it turns out to be the x direction, just shift the orientation so that that becomes your orientation of the magnetic field, and that becomes your Lz. So that the magnetic field will have an ML times mu b times b, okay, in it. So that is one thing. So you cannot know all of them. Since you cannot know all of them, pick one of them and call it the z-axis. And that's exactly what we do. Okay. So the other two, we don't know them because of Heisenberg. That's one thing. But in the same time, the magnitude of L commutes with all of them. L, you can find it if you know the other components. That's why we were able to find also L, the actual length of the vector itself. So this is, in general, some of the properties and why, if you're wondering, what happened to the Lx and Ly? Well, you don't know them. if you know one of them, which is LZ in this case. Since you can only know one of them, that's the one in the direction of the magnetic field. So take that and be done with it. I drew this picture for L equals to 1. For L equals to 2, it looks a little bit different. So you can do that. You can think about it. For L equals to 2, in this case, big L is going to be square root of 2 times 3 times h bar, or square root of 6 times h bar. And in this case, ML is going to be 0, or plus or minus 1, or plus or minus 2 h bar. So you have 5 values in here, and you can find the different angles if you wish as well. So you will again, the magnitude of the vector is square root of 6 h bar. It's easy to start with the ML equals to 0. So imagine this is square root of 6, which is something like 2 point something, okay, h bar. Then you're going to draw equal distances, or you can actually do the math in here. It's very simple to find the first one, for example, for L equals to 2. For ML equals to 2, I'm sorry. So this is ML equals to 2, 2 h bar. So 2 h bar divided by square root of 6 h bar. So at the end of the day, this will be this cosine of this angle, theta. So you can find what that angle is. And then you do the same thing for the second one, which is ML equals to 1. So this becomes an h bar. So the second angle will satisfy the condition cosine of theta equals to 1 over square root of 6. And this one is 0. And the others, you can find them by symmetry. And that's it. So that's in a nutshell how the orbitals are going to look like. Make sense? This math, at least geometry? Yes, everybody? Or we still have people who are not here now? Does this geometry make sense to you guys?
Yep.
Okay, very good. So you can find all the different angles at will where this angular momentum is actually pointing for different values of ML. Okay, the magnitude is always fixed. Okay, it doesn't change. This is not the question of the pre-test though, and the post-test, if you guys remember. The pre-test gave you n equals to 13 and wanted to know how many potential electrons I can put in this level. I did not mention the exclusion principle, but I'm going to mention it quickly. In the exclusion principles, because of the spin 1/2 property, the wave functions turn out to be antisymmetric. And they're the swapping of particles. And that leads immediately, if I have a particle in state 1 and particle in state 2, and that means that this one is just off by this factor of -1, which means that if I have 2 electrons in the same quantum state, I can swap them, but if I swap them, the 2 particles are indistinguishable from one another. So if I move this value to the other side, that means I have 2, this is algebraic equation now, the 2 wave functions add up to 0, which means that the wave function, the only acceptable wave for it is 0. Because of the antisymmetry in here, 2 particles cannot exist in the same quantum state that have this spin half integer. This is not true for the spin integer. Like for example, the photon and other particles. For when the spin is integer, then in this case, the function is actually symmetric. And they're the swapping of particles. And in that situation, what that means is psi of 1, 2 is the same thing as psi of 2, 1. So if I am talking about the same state in here for the 2 different particles, I can write it as this way, which is fine. Regardless of what psi is, this is perfectly legitimate. So 2 full integer particles can occupy the same state. Those are called bosons. And bosons are like the case, for example, of photons. Actually, a helium also behaves as a boson because all the spins cancel and everything else, so it has a full integer spin, 0 actually. And also some other particles which we're going to meet down the road, okay? So some of the particles that are bosons, they can behave this way. And they have integer particles like the electrons, the protons, the neutrons, and some other elementary particles that we're going to see in there. They're actually called thermions. Thermions are antisymmetric. Their wave functions are antisymmetric. Therefore, they cannot occupy the same state at the same time. Meaning, I cannot have the same N and the same L and the same ML and the same spin value for two different particles. So one of them has to be different, no matter what. So this is called the Pauli exclusion principle. Have you guys heard of it in your chemistry class?
I heard it in chemistry.
Yes, so this is the Pauli exclusion principle, and it's critical for this whole periodic table that we're going to discuss right now. And it's based on the symmetries and anti-symmetry in the wave functions, that's all. So for the pretest, it tells you have n equals to 13. And it wants to know how many electrons can you put in there. The answer obviously should be 2 times 13 squared. Okay, or 2 times 169. 9 times 6 is 18. 2 times 9 is 18. 2 times 6 is 17. And 2 times 1 is 2. Okay, no, 3. 2 times 1 is 3, no? So it's 378, because you have to carry that number from the other side. So that should be the correct answer, I think, okay? But the answer, the formula is this one, so it's always 2n squared. Let me show you where this is coming from. Obviously, for n equals to 13, L can be 0, 1, 2, all the way to 12, correct? Yes? Yes or no?
Yes.
Okay, very good. So ML then can be 0 or 3 in this case, 0 plus or minus 1, or 5 in this case, 0 plus or minus 1 plus or minus 2, or 7 the next time around, or in here I have a bunch of them, 0 plus or minus 1 plus or minus 2 all the way to plus or minus 12. So all of this are potential values times 2, hence that number that I was talking, because in each one of these states I can have a spin up or spin down particle. In the ML equals to 0, I can have 2 spins. I can have a spin up or spin down. So that is 2 values. In here, instead of 3, I have 6 actually. So I have 2 in here, I have 6 in here, I have 10 in here, and so on and so forth, all the way to here. I don't know how many I have. I really have to count each and every one of them. So here is the formula then. It's this odd numbers that I have to add all the way to n minus 1 times 2 at the end of the day. So the number of allowed states are going to be 2 times the sum from L equals to 0 all the way to n minus 1, where n is this number that was given to me, up to L plus 1. Because as you can clearly see, when L is equal to 0, I only have 1. When L is equal to 2 or to 1, I have 2 times 1 plus 1, which is 3. And so on and so forth. 2 times 2 is 4 plus 1 is 5. So that's the number. But don't forget the 2 that is coming from the spin, that's all. So this is the formula really I have to do. Obviously, I can break down this sum into 2 sums. So it's 2 times the sum of 2 times L from L equals to 0 to n minus 1. Plus, and here I have to add numbers from 0 to n minus 1. I have n numbers. All of them are 1. Because from 0 to n minus 1, it's actually n. It's not n minus 1 because I'm counting the 0. This is a 0 base. So this is actually n, that's all. So all I'm adding is 1 from 0 to n minus 1. Make sense? Yes? This
Yes.
sum? Okay, so now I'm going to add L integers from 0 to n minus 1, that's all, and multiply them by 2. So if you guys remember, This problem was given to Gauss when he was actually in elementary school, and the teacher, to punish him, asked him to add the numbers from 1 to 100. So all he did was multiply 100 times 101 divided by 2 and gave her the answer right away. So she thought that she punished him, so Gauss came up with the answer. So this is the sum actually of n minus 1 times n, that's the n plus 1, this number times this number plus 1, which gives you that, divided by 2, okay, plus n. Obviously, the 2 cancels the 2. The n is a common factor in here, and it will have an n minus 1 plus 1, which is n. So that's why I wrote it 2n squared. So they gave me n equals to 13. I'm not going to add up all of these numbers. I don't have the time for it. All I have to do is multiply 13 by itself, and then multiply it by 2, and I have fully told you how many states there are in there, in that energy level of 13. N equals to 13. So the fact that they gave you a big number, they didn't expect you to actually do the actual calculation. So if n is equal to 10, then it should be 2 times 100, which should be 200 exactly. Make sense?
Yep.
Okay, so this is the pretest that I promised that you guys will discuss. Okay. And the other thing also, you will be given a bunch of choices. At least that's what was given in the pretest. And there were more odd numbers than even numbers. Just because of the exclusion principle, you know that the odd numbers are going to be excluded immediately. So you really didn't need to do even this formula, because there were a bunch of them. I think they have 5 choices or something. 3 of them were odd. So those you don't check them at all. So it's only the 2 even numbers that were given to you that you need to think about them. One of them is ridiculously high or ridiculously small, and the other one is just the right order of magnitude. That's probably the one. You didn't even need this formula at all. You just basically, you could have used the educated guess and come up with the correct answer. So this is for the pretest question, okay? So now this is where we are right now then in terms of the model. We have N, L, and S. So let me, first of all, before I get into the fine structure, I need to talk about the periodic table. And so that you think that I don't cheat, I bought my own. I have my own, okay? I have my own periodic table, okay? So Mendeleev, when he was basically going through these things, and then there was a pattern actually that was discovered before, but now the picture fits beautifully. Let me go back into the Spdf orbitals. Don't ask why these names are called this way. They have no meaning, okay? And you must have seen this one also in chemistry, didn't you? For those who took chemistry? Yes?
Yep, I remember
Nobody?
that.
Okay, so L equals to 0 is always the S level. Lowercase s, okay, because sometimes there is a different s in here that needs to be contended with. L equals to 1, that is going to be your P. L equals to 2, so it doesn't matter what n is, okay? L equals to 2, that is Spd. And then L equals to 3 is going to be your F level or F orbital. And then L equals to 4, G. I don't know if we really get into H or not, but let's write it. L equals to 5, H. Okay. In this representation, N always is indicated in here. Okay. So this is the N preceding the numbers, because you could have 1s, you could have 2s, you could have 3s, depending on what N is. Okay. So this is basically how we're going to do that. So if you're given an element, okay, the element has to be put in the sequence of the increasing energy levels. And you have to know certain order. The 1s level has a higher energy in terms of negative number, that means it's a deeper energy. Then, for example, I have the same periodic table in here so that you guys see. I know some of you, when you come look at the recording, you see only the shared screen. So let me share with you how this thing is represented in here. Okay, I'm looking at the camera. So again, it's in here. So the 1s level comes in the bottom, followed by the 2s level. It's this one in here, where the electron where the state is in here. Then followed by the 2p, then followed by the, I can't even read that in here, the 3s, then the 3p, before getting into, then the 4s, before getting into the 4p, there is actually the 3d. Okay, so that is the sequence in which you really have, when you're putting electrons, you really have to see where is the lowest energy level. The first electron, that is where you're going to put it. The second electron, you're going to put it next to it with a flipped spin, that's all. So that energy level now is full. Then you come to the next one, the third electron for lithium. Then what are you going to do in this case? You're going to come in here. The 1s is full. So you're going to jump up to the 2s. So we're going to put one electron in there. Then for beryllium, you're going to take that element in here, the next electron, and you're going to put it also in the 2s. So now you have 2 electrons in there, but with flipped proton. Remember, n equals to 1 in here, n equals to 2 in here, and this is n equals to 2, 3, and those are the indices that go with it, okay? And the L is equal to 0 here, and L is equal to 0 here. That is the S value. And the P is L equals to 1, actually, okay? For L equals to 1, you have 3 states. ML equals to 0 in between, ML equals to -1, and ML is equal to +1. But then you have, don't forget the spin. So as you are filling the states, the next electron go here, the next electron goes in here, and the third electron in here, and then you start flipping. Okay, the electrons until you fill the 2p states. So the 2p states can have 6 in it. Because of this fact in here, ML is 3 times 2, that's 6. Remember the formula I just gave you? It works beautifully in this case in here. Then the 3s comes in, and you fill it with 2 electrons. Then the 3p and the 4s, then instead of going to the 4p, you're going to go to the 3d. As a matter of fact, you jump from the 3p, instead of going to the 3d, you go to the 4s. Hence, the periodic table has a periodicity in it also, and you have this jumping, as you can clearly see. You're filling the d state now in here, okay? You're not filling the p state. So this is the p orbital. This is your p orbital, and now you're doing the d orbitals. Of course, you have the s orbitals in here, okay? And then at some point you get into higher and higher levels. Okay, these are the groups. Okay, group 1, that means they have 1 electron at the end that can interact in chemistry, that can do whatever chemistry you like to do. Okay, this 2 electrons can do the chemistry, and in here 3 electrons. So the group are numbered actually, and they have numbers next to them, and each number corresponds to the active electrons. So the group 4 in here, and then there is group 5 and so on and so forth. One thing that I want you to pay attention to is the silicon and germanium. Actually, both of them are group 4. Carbon and all of these ones in here are also of group 4. And in group 4, when you're doping them, and this is talking about chapter 42 now, okay? So it's talking a little bit ahead. When you're doping them, you have to look at the elements from group 5 or group 3, okay? So if you take gallium, for example, and you mix it with silicon, that is basically you have an alloy now that is actually a semiconductor of a certain type. Versus if you take silicon, for example, and you dope it with phosphorus, which is a different, this is group 5. That means it has 5 electrons in the outer shell that can participate in chemistry. This one, group 3, that has 3 electrons that can participate in these things. Okay, so let me go back into the sharing. I know you had this discussion for those who take the chemistry in the chemistry class, and you probably got sick and tired of these things, but I'm just going to share with you guys so that you can see the power of these arguments in here. So again, you start filling the orbitals as they go. So 1s2, then the next one is 2 S2. So this is your helium. Okay. I'm sorry, helium is 1s2. What am I talking about? Actually, that's beryllium. So this is actually helium. Okay. Then 1s2, 2s1, that is actually lithium, and then 2s2, and then you start moving to the higher levels. So basically the next orbitals, 2s2, 1s2, 2s2, and then you're going to have the 3p6 in this case, and so on and so forth. If you look at this level in here, for example, 2p6, did I jump? If you look at this level, for example, it corresponds to n equals to 2. And for n equals to 2, yes. And for n equals to 2, L is equal to 1 or 0. And this is your 0. And this is your 1. And then in this, if we are concerned about this in here, that's what the question is. How many electrons can I put in n equals to 2? Well, in this case, I'm going to put 2 times 2 squared, which is 8, okay, as it should be. So that formula still works in here too, okay? If you're asking, for example, for n equals to 3, then in this case, it's going to be 2 times 3 squared, which is 18, and so on and so forth, okay? But don't forget the previous electrons. We're not asking about the previous energy level. So this is the periodic table. Hopefully you guys are clear on this, yes?
Yep.
Yep.
Okay, very good. Okay, so we're in good shape now. There is one thing I started talking about, but I really did not go in detail, and that is the work of Mr. Dirac on the spin. When Mr. Dirac basically did his algebra, he found that the mu z actually is equal to, it's called QED, the theory really, quantum electrodynamics. When he was trying to mix electricity and magnetism, namely electrodynamics with the quantum phenomena, knowing that in Maxwell's equations are invariant actually in the Lorentz transformations. So he added that to the requirements for Schrödinger's equation, and he came up with the spin, and the spin value that he came up with exactly is equal to -2 times the same value that we found earlier, which is E over twice the mass times SZ, okay? Well, the experiment did not agree with him. The experiment found that this number is not 2, called the gyromagnetic ratio, is not 2, but 2.00232. So there was something missing in his calculations. So what they did then later on, they included somebody else, I forgot the name, included the interaction in this case with the higher level order, if you wish, corrections, using the alpha term, which I'm going to define right now. Okay, and he found a higher value than what Mr. Dirac has found. Okay, obviously that calculation later on, Mr. Feynman noticed that why do you include one term? You can include as many as you want. So perturbation theory developed based on that coupling term, and that the value right now, as we know it, I'm going to copy it. I don't know it. Okay, so it's a very long value. This is the calculated and the theory, so that you guys understand the calculated theory and also the experiment, and see how much they agree with one another. So this is the correct value now that we know of: 002319 3043 6182. Can you imagine a calculation that gives you this level of accuracy with the experiment? I mean, look at how many decimal points after the 0. After the decimal point, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There is an uncertainty about this number, but the theory that gives you that much precision must be extremely, extremely accurate. This is what the QED is. Quantum electrodynamics. This is the combination of relativity and quantum mechanics. At that level, of course, there was problems, conceptual problems between the two theories that are until today irreconcilable. Among them, the uncertainty principle and the fact that this is not correct in terms of classical, in terms of relativity. So this thing was so beautifully, immaculately accurate that QED is known as the most accurate theory ever. With anything else, doesn't matter, physics, anything that you can think of, nothing can match its accuracy and its prediction power because of calculations like this, using something called the Feynman diagrams. Obviously, it's perturbation, basically, but it leads to this accuracy in here. So this value is from your book, okay? So this is now the coupling due to the spin. So this is S. What am I putting as Z? That's museum. Sorry. This is the magnetic dipole moment due to the magnetic field. Okay. So which may lead me to another point in here. So the value of S, by the way, is equal to square root of 1/2 times 1/2 plus 1, same thing, times h bar. So this is the actual angular momentum due to the spin. The spin angular momentum is equal to square root of 3/2 h bar. And again, the two projections are the same fashion. So SZ can be either positive or negative 1/2 of h bar. Okay. It cannot be anywhere in between them. It cannot be any other value. So those are the only two possible values. It cannot, again, have SX and SY for the same reasons. I cannot have LX and LY if I know what LZ is and what SC is. Okay. So this is the same thing that we were talking about earlier. So let's now recapitulate or add the two things together. So the total angular momentum is actually a vector that is equal to the sum of these two vectors. So this is the total angular momentum of an electron. It's the sum of these two values as a vector, because it's still as a vector. So really, I should be concerned with J, not L by itself or S by itself in all of my interactions. In one particular case, and the calculation gets a little bit more complicated at this point, to get into the Feynman diagrams, you really need a lot of math that is way outside of the scope of this class right now, is that the electron, because of its internal spin, will interact actually with the proton. So in other words, the proton itself is actually wobbling in this situation. From the vantage point, if you are a person living on the electron planet, let's say, for example, you go on top of the electron. For you, it's the electron, the proton that is spinning, not the electron. You are sitting on it. The same thing, for example, when we are sitting on here on Earth, we see the sun rise from the east and go to the west, day in, day out. So for us, we assume that the sun is moving and moving in a circular path. So because the sun is moving in a circular path, I can calculate its the magnetic dipole moment in this case, because it's a proton, it has a charge moving around the electron, and that will create a magnetic field in the location where the electron is. So there is an intrinsic connection between the spin orbit coupling. So imagine, as I was saying, and the calculation goes like that, the electron from its vantage point, it's sitting still, has its own intrinsic spin, its own magnetic moment, if you wish, dipole moment, and the proton is moving around it, just like the sun moves around the Earth. So because the proton has a positive charge now, E, positive E, so that is going to create a current, I. And then I can proceed by finding the mu for that, okay? Once I find the mu for that, basically, actually, I can find the magnetic field using Ampere's law. So once I find the magnetic field due to this one, due to the proton is because it's a charge in motion. So that means it's a current in motion. That means I can use Ampere's law to find the magnetic field in that point. Once I find the magnetic field, then this spin and this magnetic field will interact. So there is an orbital motion of the electron going around the proton, but I can attribute it from the vantage point of the electron as being the proton moving around it. Okay. In doing so, you have a charge now in motion that creates a magnetic field in that point, and then we're back into the energy. In this case, that should be shifted by a value of, in this case, mu of the electron, the intrinsic mu due to the spin actually, times the b of the orbital motion. So this is the b created by the orbital motion. Does this point make clear? Is it clear, or should I explain it a little bit better?
I understood it. I don't know if.
Yes. So basically, here is the effect. You're in the electron. The electron, from its own reference frame, it's not moving, it's stationary. Like, for example, right now, we think the Earth is not stationary because we're sitting and talking about in our chair. So the Earth is stationary. So from our vantage point, the sun is actually moving. And the sun, imagine if it's a charged particle, it's going to create a magnetic field from where we are because it's a charge in motion. That's exactly how you can think about it in terms of the electron. So the electron is sitting still, thinks that the proton is moving around it, creating a magnetic field in its location where it is. But the electron has its own intrinsic spin. It has its own intrinsic magnetic dipole moment, if you wish, and that comes into mu times b. Now, the energy, what it is going to be shifted, even if there is no external magnetic field. So this is even in the absence of an external magnetic field. Absence. So even if we are not inside an external field. Absence of external B. So even if that, then is an intrinsic value, there is actually a coupling that is going on between the spin and the orbital motion. And that leads to corrections in terms of the value of the energy, overall energy of the hydrogen atom. So it's no longer dependent only on the value of n, but it depends on this value of J now. Remember, J is a value now in magnitude is going to be given by L plus or minus 1/2, because the spin can be in that value. So J, since it's the sum of these two vectors, depends on L first. L is shifted up or down by this value of the spin, okay? So that is basically the value of J. So now this is the value of J. We need to find it first. So each level, if you wish, is going to be broken down into two. L equals to 0. This is the S levels. They will have 1/2 only, okay? Plus or minus 1/2 in absolute value. So the value of J will be 1/2, okay? For L equals to 1, which are the p orbitals, by the way, then in this case, I will have the absolute value of 1 plus or minus 1/2. So either 3/2 or 1/2 for the J value. Again, for L equals to 2, namely D orbital, then in this case, it's going to be 2 plus or minus 1/2. So in this case, it's going to be 5/2 and 3/2 and so on and so forth, okay? So each orbital will be broken down into two values, potential values. So the energy is going to be negative. This is important, okay, that you guys remember it, divided by n squared. So this is the old value with the correction that is coming from this coupling, plus. This is the term I promised earlier that is going to be introduced, and that is alpha squared over n squared times n over J plus 1/2 minus 3/4. So the derivation is really, really not easy. It's very long, but this is where this term is. The term alpha is a dimensionless number, and it's equal to about 137. I mean, 1 over 137. Okay. It's actually coming from the coupling of the electrostatic force and the nuclear force, the strong nuclear force. Is it H bar or is it H? I don't remember. H bar C. Okay. This is dimensionless number that tells me how much the nuclear forces basically impact the electrostatic forces, because all we've been dealing with actually are electrostatic forces. So in this case, it's a tiny number, as you can clearly see. It actually has a numerical value of 7.3 times 10 to the negative 3. So it's a small number. Furthermore, it's divided by n squared. So the higher you go in the energy levels, the smaller this value is. So the actual value of the energy, actually, when we said it did not depend on J, it does. And when we said it does not depend on L, it does really. L and S, they're combinations. So when we do now the spectral lines, we really have to take this into account. And this is where that anomalous Zeeman effect is coming from. This is called the fine structure. First of all, this is the fine structure constant. Okay. This is one of the constants of nature. Again, it links the charge of the electron with the permittivity of the medium, the speed of light, and the h bar. So all of this are constants. Okay. So it's a constant, and it has no dimensions. It is a constant that gauges the strength of the nuclear forces versus the electrostatic forces. And this constant is so truly chosen for our universe so that our universe functions the way it does. Otherwise, nuclear forces, if this value was stronger, will be too weak, or if it's too strong, it's going to be too strong. So the physics and chemistry will be completely different. So this is a constant that is actually has a major impact. Among other things in here, the spectral lines are going to have many, many different values depending on N on J. Actually, there is a problem that we're going to do. Is problem 53 deals with this thing, and you will see that there is all kinds of emissions that are going to happen between two different levels of N. We're going to take N equals to 5 and N equals to 2 for the case of the hydrogen atom, and you will see how that looks like. Okay. So this is an important formula for your homework, for your exam, for your discussion later on, for everything else. So we're going to have to deal with this one. So the energy levels, this is the bottom line, and you can reproduce it if you want to, do not simply depend directly on N. They depend also, I was going to say they don't directly, yes, depend on L, the angular momentum, but they indirectly depend on it through this value of J. Remember, J is this vector, which is the sum of the angular momentum and the spin. And its value is always given by L plus 1/2 of L, which is always, they have to be positive, because we're looking at the magnitude of J. We're not looking at the direction. So its magnitude is given by this absolute value expression. And that is going to give me the different corrections. So the energy levels, as we know them from Niels Bohr, even intrinsically, even without anything else, they are not only dependent on N. That's why we were seeing the anomalous Zeeman effect, even in the absence of a magnetic field. Okay, and that is because of the interaction of the electron spin and its orbital motion. So it's called the spin-orbit coupling. You guys know what to do for the discussion is to make sure that you're aware of this fact, because sometimes you get into the moods basically of writing the expression just in terms of the n number, which is fine, but now you have a correction term coming from this coupling term. Make sense, everybody? Yes, no? Guys, are you here or not?
I am here.
Okay, we still have two minor issues that we need to deal with, and we're done for this unit, so I'm going to mention them. Is this too much, or we're good in shape, or we're proceeding well? We still have actually 3 items. This is the X-ray. The last one is the entanglement. Entanglement is really more of a, wouldn't have much. We'll see. Are we good, guys? Can we continue?
Yep.
Okay, very good. Okay, very good. So basically, here is a question then. Remember when we did the hydrogen atom, somehow so now we're going to talk about many atoms, okay? So everywhere we were looking at the product of the charges for the expression, for example, for the energy, which is really coming in here in the 13.6 electron volt, because that product is a product of E squared, and that E squared is coming from the number of electrons and number of protons. But in the many atoms, you will have Z of them on each. You will have Z protons and Z electrons. So it looks like this formula now, everything else will be corrected by Z squared. Okay, but that is not true because, for example, it's going to give me ridiculous radii and it's going to give me some nonsense results. Okay, so what's going on? There is a screening effect. For example, let me talk about the lithium, for example, which is easy because we have 3 protons and 3 electrons for lithium. We have neutrons, forget about the neutrons for right now. So the inside, you have 3 positive charges, and the outside now, you have 3 electrons charges, 3 electrons. So 2 of them are in the s orbital. One of them is pointing up when it's spin, and the other one is down. Usually we don't write them on the same side, but that's fine just to see them, okay? They are not point particles, they're actually occupying the entire orbital, which is like a sphere, okay, smeared around the electron, around the proton. As a matter of fact, I know I did not do the orbitals. The wave function looks like it's peaked somewhere around A naught, and then times, in this case, N, and then, no, the first one is not, just A naught, okay? And then the second one is actually also smeared in there. So there is actually, they spread in and out, okay? So there is a little bit of overlap. So the second electron is somewhere in here. The third electron, I should say, in here, in this orbital in here, which is also spherical in shape, okay? But this electron in here, that is in the outer shell, namely the 1s electron, the 2s electron, that one sees basically a net charge of positive 1 electric charge. Because if I apply Gauss's law in this case on it, Gauss's law says the net charges. So if I want to find the electric field in here in order to derive my potential, for this one, it looks like the net charge. So I have 3 positive charges and I have 2 negative charges. So at the end, I have a net positive charge in this case. So there is this screening that makes it so that I cannot really write the Z squared in here, but instead, for each electron that I'm going to account for, I have to come up with an effective value for Z that depends on the atom. So the problem is a little bit more complicated in general, and it's not as if I have to just replace the values in the hydrogen atom for the next atoms. That's why we have that effect. So we have a screening effect. So we cannot really plunge them all with the same values. Okay. So this is the argument that I'm going to make in here, and it's based on this fact in here in Gauss's law. So in other words, this electron will not see all of the 3 protons in this case, but sees only a net value of one of them because of the cancellations of charge between the 2 electrons that are already inside the 1s2 orbital. Okay, so that's why you see that. Okay, so that is this effect. So the screening effect is an important one in here because it determines the size of the atom. Because if it's really 3 protons pulling on that electron, they should pull it closer, and the size of the lithium atom should be smaller than what it is. It is smaller than the hydrogen atom to begin with, in terms of. No, let me back up a little bit. The beryllium, which is the next one, with Z equal to 4, is actually pulling on more than the lithium. So the beryllium should be smaller in size than the lithium, because I cannot really compare the 1s, for example, with the 2s. But the 2s and the 2s should be fine, or the 2s and the 2p should be fine, because I still deal with the same level in terms of the energy. Because as you saw earlier in the graph, the energy levels are too wide in here at that point. But for the beryllium and the lithium, the comparison is 100% justified, because for the case of the beryllium, in this case, they have 4 protons pulling on the electrons, so they shrink the size of the atom slightly less than that of the lithium. In this case, if I do the same analysis, for example, for the lithium, I might be tempted to think that, hey, I have 3 protons pulling on it, therefore the size should be smaller, the physical size should be smaller. And that's not true, because, yeah, it's going to be smaller, but not that small, because of the screening effect of these 2 electrons. Okay, so this is in terms of that. And the last point in here in terms of your homework assignment, honestly, and the problems, is the one that has to do with the X-ray spectra. Remember when we did the Bremsstrahlung, what do you call it, the breakage, basically emission of the electrons, we found this following pattern. So this is the wavelength, and this is the intensity of the emitted spectra. So this is lambda. There is a cutoff frequency, okay, cutoff wavelength, below which we cannot see any kind of so there is a lambda cutoff in here. You need a minimum amount of energy for you to excite to get this effect. And then the spectrum look more or less continuous like this one, okay? And then it starts to diminish. However, there is a line in here, a sharp line. They called it K alpha. And then potentially, depending on the element, there is actually K beta. Potentially also more, K gamma, and so on and so forth. Okay? But definitely there is always K alpha. So this is a longer wavelength than this one or that one, okay, for the X-ray emissions. Now we have an understanding where that is coming from. When the electrons are bombarding the material, the tungsten, for example, what happened in this case, some of them get so close that they excite one of the 2 electrons in the 1s level. So one of them is kicked out in this case. So there is an empty space in here. So one of them is here now. So there is an empty space now for a transition to happen, because you have electrons sitting in the 2. This is n equals to 1. This is n equals to 2. By the way, n equals to 2, they all have the same energy level approximately. So in this case, this one will transition back. This has the least amount of energy, because the one that transitioned from n equals to 3 will have a higher gap to jump. In other words, the difference in energy in this one is higher than the difference in energy from n equals to 2 to n equals to 1. There is also the potential that even from n equals to 4 comes in jumping, but the gap in here starts to shrink, because remember, the formula that we're going by is negative 13.6 over n squared. So as n equals to 1, so it's negative 13.6. But as n equals to 2, it's negative 13 over 6 divided by 4, which is 3 point something. As n equals to 9, this is 1 point something. As n equals to 4, this is actually 0 point something, and so on and so forth. So the gap starts to shrink between them. So what we see usually is the low energy one, no matter what. And this is the easy one to transition to. That's why its intensity is high. Okay? Because that is the one that comes in falling right away. Okay? Raining on the n equals to 1 level. So these are called the K shell, actually. And this is the L shell. So most of the transition are from the L shell to the K shell. If you think about it as a shell structure, that is actually how the atom is thought of in this case. There could be from n equals to 3. But that is actually a low probability. That should be higher energy, less wavelength. Remember, the wavelength and the energy are inversely proportional. So if that means less energy for this transition, the lambda in this case should be higher. Then if it's more energy for the n equals to 3 down to n equals to 1, then lambda should be less. Indeed, K alpha will always appear in the diagrams in here. It's a sharp peak called the characteristic emission. And this is And K beta sometimes also comes in, and it's also characteristic of the element, meaning they change depending on the element. Okay. If you're not using tungsten, you're using another metal, you're going to have a different value for it, shifted. Okay. K beta, but you will always have that spectrum. And again, the cutoff also depends on the material, because you cannot have any kind of emission unless the initial energy of the electron is high enough so that it can bounce back. And that is what the cutoff is. Okay. So that is, I'm sorry. Yeah, when it comes in and hits the atom, it comes back to it. Okay. So that is, no, actually it's fully absorbed. What am I talking about? This is an electron. It's absorbed. Okay. It loses all of its energy, basically. So this is the highest energy that you will have. And then those that are deviated, they correspond to this other spectrum. And now the others are just right frequencies so that they can excite actually the electrons, and those they are seen as these spectral lines. So this is basically the pattern. When they plotted this function as a function of z, this is how it looks like actually. As a function of z minus 1, actually, the frequency, the square root of the frequency as a function of z minus 1. So in other words, it looks like it's a function of z squared. So it looks like it's a line now for the different materials. So again, it seems like, and this is what's going on in this case, the frequency, which corresponds to the energy of the electron falling back on it, will see all of the z electrons, z protons, screened by that electron that's still there. That's why you ended up with z minus 1 and not z. So when it falls down, which corresponds to the energy, which corresponds to the frequency, then in this case, that frequency and the z are proportional through this relationship, okay? And that makes sense to us then in this case. So this is the K alpha. Remember, the K alpha is always n equals to 2 and n equals to 1. So we know the values, except we have to make the corrections between for the different values of n, if at least at a hydrogen atom, except now we're going to include other effects to it. So the value should be 13.6 for n equals to 1, and 13.6 divided by 4 times z minus 1 for the different elements in here, which is going to be about what? Something like 10 or something electron volt times the z minus 1 squared. Makes sense, at least in principle. What's going on in here? Yes? Okay. You guys need to review these problems. Oh, I still did not give you the problems that we need to talk about. How do you guys feel? Okay, the problem I'm going to discuss is really a long problem, and it's going to take a long discussion, but I'm going to give you the problems anyway. And we probably have to touch base with them next time when we meet, before we get into the new topic in here. So the problems are from this unit are, as I mentioned before, problem 59, 60, let me write them down. 59, 60. 59 is really an easy problem to talk about, okay, just in principle, okay? But it's a good idea to go through the exercise to understand what's going on with it. 60 is a very important problem, okay? It has to do with the fine structure also. 4153, the problem 53 from page 1405. 53 is also about the fine structure in this case. So both of them are extremely important. Problem 44, problem 51 and 52. Problem 30 and 31. Is this enough? And 63 also. Should I repeat them?
Oh, yes, please repeat it one more time.
Okay, 30 and 31 from pages 1403. 44 and 51 and 52 from page 1404. 44, 51, and 52. A lot of these problems are actually easy. I mean, one of them probably that's we're going to spend a lot of time talking about is 53 from the next page. 53 is a long problem. 59 is really, I think I already talked about it, but I'm not going to talk about it anymore. Basically, what happened to the SPDF model when you have a spin that is actually not 1/2, but 3/2. Okay, so in this case, the 1s level needs 4 electrons to fill, because you will have positive 3/1/2, positive 1/2, negative 1/2, and negative 3/2, all of 4 electrons. So you go all the way to beryllium before you find a fully filled quantum state. And then the next one and next one. And they ask you on that problem to see what happened to sodium. Sodium, of course, is equal to 11. So in this case, 4. And the next one is going to be, again, the 2s state, but the 2s state will require 4 electrons too. Okay. And then the 2p state, so they're going to barely fill their first 2p state. So the configuration will be completely different. The chemistry will be completely different in the universe where the spin number is actually 3/2. So that's problem 59. So I'm not going to come back to it. Problem 60, next to it. And problem 63 is because we do sometimes problems like data problems. So do not exclude those type of problems from any exams. We potentially could have a data problem where you're going to analyze stuff and do graphs and things like that. Okay. How do you guys feel about these things?
I'm so excited.
There is something I didn't talk about, and that is the entanglement. Okay, and this is something that is actually a problem. In non-quantum mechanics physics, basically, this becomes a major problem, because here is the situation. If you start with a quantum state of 2 particles that are interacting with one another, for example, the 1s state for a helium atom, for example, okay? You have one spin up and one spin down. And if somehow one of those spins gets entangled from the other one and moves away from it, here is the thing. You could potentially measure the spin of one of those electrons and find its value. Once you find its value is up, for example, 1/2, run it through Stern-Gerlach, for example, you find that spin is up without doing any measurements. And instantaneously, you will know the spin of the other one that you didn't make measurements for, even if it's miles away or hundreds of miles away or light years away from the first one. So it seems like, and the quantum state, by the way, before you're doing the measurement, is a superposition of the 2 values. So the spin, as it separates, when you do the spin function in this case will have only 2 values, either up or down. So in this case, the value could be either spin up or spin down. But when you do the measurement, the wave function collapses on one of those 2 values instantaneously, and whatever you find, that is the value of the spin value. So if it turns out to be up, the other wave function that is on the other side of the universe would have collapsed also immediately on the spin down. And this created a problem, because it seems like we can communicate, we can have information. If we agree, for example, you and I, before splitting this helium atom, that if you measure the spin and it turns out to be an up spin in your case, then do some action, whatever it is. For example, leave the planet or destroy the planet or do something about it, okay? And if you find it down, do something else, whatever it is, okay? That we discussed that you need to do. Take a break, for example, or go to lunch or skip lunch or do whatever, something, okay? We agree on an agreement. So now we're separate at faster than the speed of light, and I do my measurement. And I find out, for example, the spin is down. So I know what happened. I have received information faster than the speed of light about what you have done, okay? Because I know your measurement for the spin is going to be up, or the opposite of what I did. So if it's down, yours is going to be up in this case. The spin that you're going to measure is going to be in the opposite direction. So in this case, I know what you have done. So it seems like information can travel faster than the speed of light, which is in violation of the theory of relativity. because nothing can travel faster than the speed of light, including information itself. So this seems to be a controversial problem because Einstein immediately objected on this one, and seems like how he termed it as spooky action at distance. And this is true in quantum mechanics. So this is still a problem for relativity. Except if you try to make really a device out of it, if you want to really make something out of it, it's really not practical. But measurements have shown that actually this entanglement, which is what it is actually can go over long distances instantaneously. So this is not something that is actually theory. It's actually an experiment too that shows that. So this is unit 41 for you guys. When we meet on Tuesday, we're going to finish the problems a little bit and start chapter 42. Okay. I hope you guys will bring any kind of discussion items. We have a lab next week also that I want you guys to focus on too. So bring discussion items to because you will have unit chapters 37, 38, 39, and 40 in the exam. Understand that chapter 38 and 39 are actually one chapter. It's the same idea flipped backward, that's all. And chapter 40 is about one-dimensional Schrödinger's equation. And also don't forget the tunneling effect and the probabilities that you calculate there and things like that. So those are the topics really in terms of the exam for exam 2. Yes, 37. No, Natasha. 37, 38, 39, and 40.
Okay, so no 41.
No 41. 41 is
Okay.
not in this. 41 is in the next exam. 41, 42, 43, and 44 are for the next exam, the exam that is coming after. So 37 is a relativity, and it's a big deal in this exam. 38 and 39 are basically the same relationship that we talked about. Okay, the momentum and how it's related to the wavelength, and also the energy and how it's related to the wavelength and to the all of that. Okay, they should be on cam. Okay, I'll have to check that then. I'll check Pearson to see what's going on. Okay, and then as I was saying, this is what we're going to do. We're going to discuss especially problem 53 because it's very important that you guys have full understanding of what's going on, and that gives you also a flavor of what's going on for both the Zeeman effect and the Zeeman fine structure, basically, because they are two, or the anomalous or the odd, if you want to call it, Zeeman effect. Okay, so we're going to have that. We have to have that, and we're going to start with chapter 42. Chapter 42 deals really with the molecules first of all, because the atoms now we're going to leave them a little bit behind us. We're going to the molecules and the different bonding structures in them. And then we're also going to molecules when they form metals, when they form actually a solid state. So we're going to have single molecules, and then in the crystalline structures, crystals, and then we're going to get into the conductors and try to understand basically normal metals. And that is when I go back into that expression that I discussed today for or actually I started on Tuesday, namely the electron or the free particle inside a box, because that's exactly what it is. So we need that expression. And we're also going to have the semiconductors. We're going to spend a great deal on the p-n junction, basically for the diode, and then also for what is it called, the BJT transistors, bipolar junction transistors, basically the NPN or the PNP transistors. We're not going to get into the MOSFET or any other kind of transistors because they're outside of the scope of this class. But hopefully with these two kinds of things, you would understand enough semiconductors so that if you're taking electronics, you will be in good shape. And we'll try to touch a little bit about the superconductivity, and that will finish chapter 42 before we delve into nuclear physics and elementary particle physics toward the end. Sounds good, everybody?
Sounds good.
We're closing in. We're almost done with all of the heavy lifting stuff, so we're almost there. Okay, I'll see you guys on Tuesday from today. Okay. and see you there.
Professor. May I? Professor, I have a
Right.
question about the lab, the resistivity lab.
Okay, the lab, which
Mhm.
lab?
Lab 5.
Okay, hold on, let me pull it, okay. About relativity, go ahead.
Yeah, question 4 under the spaceship.
Yes.
What are we supposed to do for that question? I don't understand it.
Hold on. Let me find it first of all. Oh, that's come on. Okay. Lab 5. Okay. Let me pull it. I thought I did. Close this thing in here. Lab 5, okay. So let me pull the lab 5 first. I don't want to download it because I don't want to. Question 5, you said?
4.
Okay, this is what you're supposed to have done, okay? So you should have done the calculations on the same page on the top, okay? Where you find from the perspective of the spaceship, okay? From the frame of the spaceship, you're going to find the front of the station, meaning the front of the spaceship, and also the back of the station, meeting the front of the spaceship, and the back of the station, meeting the front of the spaceship, and the back of the spaceship, meeting the back of the station. So there are 4 events in here that I need to worry about. The front of the ship with the front of the station, from the vantage point of the space station, okay, from that reference frame. So the front with the front of the station with the front of with the back of the ship, and then the back of the station with the front of the ship, and the back of the station with the back of the ship. So there are 4 events. That's why you have in here so many fields. Some of them have already been given to you, namely equations 14, 15, and then you're going to write equations 16, 17, 18, 19, 20, 21. Based on that information, you're going to, first of all, discover that the simultaneity in this case is not respected. So in other words, to begin with, in the space in the frame of the spaceship itself, you will be inside the station when both of your front and back are actually inside the station. But that is 2 simultaneous events. In here, you will see that the back of the station will cross from the space station perspective. The back of station will cross in before the front will cross out, before the front actually goes into the front of the station. So that is how we resolve this issue. So you have 2 calculations to do. So I assume that you did the first one. So the first one is kind of easy, because as the ship is going in, so its length is shrunk, so it's going to fit in. There is no problem. The second one, actually, the station is the one that is shrinking. So in this case, the back will go in. In other words, they are not simultaneous. In other words, the ship will fit in, not in the same time, according to the station perspective. Okay, but from the other perspective, you're going to find it fitting. So you really have to do the calculations first, and then be able to answer question 3 and 4, and find the time delays and the positions of the 2 locations. Did this somewhat help?
No.
Okay. The first calculation, the first part. Okay, let me go into let me see if I can share this thing with you guys. Okay, let me go back into the let me share it with you. Share. Okay, so this is the space station, stationary, sitting in the space station, looking at the ship coming in. Okay, the ship, because of the length contraction, appears to be shorter. Make sense?
Yes.
Because it appears shorter, it's not going to be 400 meters in length, it's going to be less. So it's going to fit in at once, meaning the front will be before the back of the station, and the back of the ship will be before, past the front of the station, because it's smaller actually in size from my vantage point sitting in the station. Make sense?
Yes.
Okay, right now, without relativity, this is 400 meters, this is 350 meters. There is no way that you can take a ship of 400 meters and put it inside, unless the length shrinks, which is perfectly fine. So this is from the space station perspective. Now, so I assume you did the calculations in here to make sense, okay? So that you found the length and you did all of the graphs and so on and so forth. Okay, let's look at it from the space station perspective. Now it has to do with the times, actually. I have to find when the time of the back of the ship goes in, and find the position, basically the different position with the different times and where they are. Actually, I have to write the formulas and I have to put them in there. Okay, so this is actually the formula. This is the actual numbers. This is the front of the space station, and this is the formula, and this is the back, and I have to put it. So this is the back of the ship, the front of the ship. This is the back of the station, and this is the front of the station. So you have all of these formulas that you're supposed to be working with. Granted, the times are not the same. In other words, this event of the front of the station will happen later. Where is the picture? Will happen later. So if I'm sitting now in the spaceship, looking at this one in here, I will see the back of the ship crossing the front of the station first, if I do the calculation, before the front of the ship crosses the back of the ship, okay? So these are not the same time as before. This is not the same as before. As a matter of fact, if I follow the length contraction, this station should be smaller in size. So it's going to be less than 350, okay, about 320 something, okay? So the station is actually smaller. But if I calculate the event when the back of the ship crosses over the front of the station, I will decide to see that this event happens before the front of the ship crosses the back of the station. So it's going to fit. But I have to do the math in here and reconcile these equations. Okay? So these are the transformations in the spaceship from the vantage point as if the other one is moving with the negative velocities, okay? Moving backward. So this is moving forward from my velocity in the positive direction. From the spaceship, everything is moving back with the velocity beta. So I use these transformations in the equations, okay? And I calculate again for the front of the ship. Because I'm sitting in the front of the ship, I'm going to give it a coordinate of 0. And the 0 in this case, I'm going to plug it into this expression. I'll find this is when that event happened. So it's going to be given by T times gamma. And obviously, I need to sub the value in terms of my reference frames because I have to find it in terms of betas, okay? So this is the formula that I need to use. So this is for the front of the ship. For the back of the ship, okay? For the back of the station, I should say, I have to use the same transformations. Remember, the station for me right now has these coordinates. Its length has shrunk also from 350 to 320. I don't remember exactly what it is. So its position is no longer the 0, but I have to give it the value of the new length plus the 0. So I'm going to use the same formula and continue in here and sub the value of t prime. So I have to put it in both values in here and sub at the end the value of t prime and sub the equation in here and in here, okay? One of them is symbolic equation and the other one is a numerical value. That's all. That's the difference between the two. So in here, there is probably a negative sign, and here there is a negative sign or a plus sign, depending on the signs that you chose. And there is a gamma factor in here and there, and so on and so forth, okay? And you repeat the same calculation. As you did with the first part, you should be able to do it with the second part. The only difference in here, as I was saying, the two events, and this is the answer to the question actually, the two events happen backward, okay? That the back will cross over before the front will pass the back of the station, okay? I don't have all the numbers with me right now, but if you want to, we can go through the details of the numbers, but it's actually this formula, that's all. That is given to you in here using Lorentz transformations, but now for the back of the station. So this is the front of the station. This is the back of the station, and you do the same thing for the front of the ship and the back of the ship.
Yeah, I have the other numbers. Just number 4 that I'm confused on the question for. I have all the numbers and everything. Yeah.
For instance, event FB happened before event DF, whereas the ship and frame event DF prime happened before FB prime. How can you resolve this? It has to do with the simultaneity is not the same. Okay, two events cannot be in the same time in this. If they are in the same time on one frame, they cannot be necessarily in the other one. Okay. It has to do with the simultaneity. The simultaneity is not observed in both reference frames. That's all. Okay. If you graph this graphs in here in the station frame, and if you graph it in the other one, you should be able to see it. Let me go through the numbers myself and see exactly if, because right now I don't have the numbers before me and it's been a long time since I did the calculations, but let me pull the numbers. It should not take a long time. And then once I do that, I will share that with you guys. Make sense?
Makes sense.
Okay, so it should be there. Okay. So, any other question? Did you resolve the twin paradox though? When is this lab due anyway?
Wait, I have a question, but it's when will we review for the test? Because you said there's a lab next week, so.
Next week on Thursday, we're going, if you have any questions about the test, because technically I really was not planning to do anything other than what we did already in the chapters, in the unit chapters. And
Okay,
if you bring a question, that would be something that I would be discussing in there about something from units, of course, from chapters 37, 38, 39, and 40. Okay. So it's due April 2nd. Let me push this assignment a little bit beyond so that we have any kind of questions. So I just changed the assignment when it's due so that we can have any and all of the questions answered for this lab. Okay. Anything else? No? Sounds good. So I'm going to stop the recording and I will see you guys Tuesday.